Welcome everybody to the very first PyPSA Python for Power System Analysis user meeting. We've never actually done this before. I just checked the Git commits. We did the first Git commit, Jonas and I, in 2015, so 7 years ago, just over 7 years ago. And we've never really had any kind of community or user meeting. So we're very happy to see so many of you here today. And the idea was basically to bring everybody together and see what everyone's doing with the tool, because as developers, we never actually get to really see who our user base is. We can see people downloading the tool, we can see people asking questions in the mailing list, but who's actually intensively using the tool on a daily basis and what they're doing with it, we never really have a clue. So we're very happy to see that so many of you kindly volunteered your time to talk about what you're modeling with PyPSA. And we're looking forward to seeing the talks. Feel free to mention in your talks things that could be improved, because we'll be taking notes. And at the end, Fabian Hoffmann and Fabian Neumann will also give a few short slides on what our current plans are for the future of PyPSA. And as you may have seen, we're also trying to raise a bit of awareness and maybe money to develop a bit of a GUI as well. So there are continual developments, and we'll try and keep you updated on those. That's actually all I really wanted to say, and I will hand over to Christoph then for the administrative and format details. So thanks.
Great. Thank you very much, Tom. I will also briefly share a couple slides from my screen. Hope this works well for everyone. So welcome also from my side to the first PyPSA user meeting. We're really excited to have a big crowd of enthusiastic energy system modelers here today, and especially pleased to have 13 wonderful speakers who will give each a lightning talk and tell us something about their work with the PyPSA toolbox. Couple words on the format and the recording. We will, for each speaker will have 10 minutes for their lightning talk, and we will have a very brief Q&A session of about 3 minutes following that, so you can already get your most pressing questions to them, and we can get some more insights from the speakers, and then we'll transition to the next speaker. After we have done all the presentations, we will have another maybe hour or so of optional Q&As that we will split up into breakout rooms here in Zoom. And we'll do the logistics at the end of the talk, see where additional Q&A exists. And we also invite each and every one of you to also possibly suggest additional discussion topics that you would like to pose to the group here. And if we have some interest for those topics, we'll also assign them to breakout rooms in the end. Just briefly for the recording, we have started the recording. We are recording the shared screen and the speaker view, so don't worry, your video is not being taped as we speak, so you can share your face with all of us. I think it's also for speakers a little bit nicer to look at faces instead of just black tiles. And we also have individual audio files for each participant, so in case you do not wish for your contribution to be added to the recording, just reach out to me after the meeting and we can remove you pretty easily. And other than that, yeah, we're really excited. And briefly going through the agenda, we will now start with the first talk. We have 7 talks and then a short break. And after the break, these times are indicative. We'll kind of go maybe a bit quicker if we can, as we have saved a couple minutes now. And then after the break, we'll have 6 more speakers, and in the breakout rooms at 12:20 approximately.
Christoph, if people want to pose a question, should they pose it just in the chat as a text, and then we can ask the person to speak out loud in the Q&A? Is that the best way to do it?
Yes, that would be nice. If you put questions in the chat, we'll raise those 1 or 2 from the chat, and that's a very good idea. Okay, and now without much further ado, we'll have our first speakers, Max Parzen and Ekaterina Fedotova. They're from the PyPSA-Earth modeling team and presenting the talk, "What the heck is PyPSA-Earth?" Max is a PhD student in energy systems modeling at the University of Edinburgh and the founder and director of PyPSA-Earth initiative. And Ekaterina is a senior researcher and data scientist at the Institute of Energy Problems and leads the Central Asia group in the PyPSA-Earth initiative. And welcome to you. The floor is yours.
Hi, thanks, Chris. Thanks for the introduction. I think we just need to stop sharing your screen. Yeah, great. Okay, is that screen sharing working?
Yeah. Okay.
Yeah. Then thanks, guys, for joining today. Today I'm presenting, as Christoph mentioned, a bit what we're doing with PyPSA-Earth, and also hopefully get some rid of confusions because we're changing the names all the time. Yeah, basically, I mean, what you see here is a logo. I just got that from, I think, OpenAI or something. You know, you can write a text, then a picture comes out. Yeah, like this is not PyPSA-Earth, for clarification. Okay. Down there's a logo called PyPSA-Earth. And what is PyPSA-Earth? Like, what's the relation here? We are basically a grassroots initiative that aims to accelerate and cost optimize the world transition to sustainable, accessible, and reliable energy with open source planning tools and open data. And just to clarify that in that context, where's PyPSA-Earth? So we have these frameworks. We're using PyPSA as, I mean, our framework where we write the problems, and then if we're adding data to that framework to represent an energy system, then we end up in this kind of models, PyPSA Europe, or the sector coupled model, PyPSA Europe SEC, or then the PyPSA-Earth model, which will also become sector coupled in the next few months or so. Then I just want to, for completion, and all the tools that I mentioned here that are on the website as well. Katja just shared, I think, in the chat, the website. But we work also on data for energy system modeling. Then we have also this open source solver interfaces and support that we're working on, and the open community. Everyone is probably familiar with the Google Groups for asking good questions. We also launched recently a Discord server, and you can enter that. It's open for everyone, free, and you can start a discussion there as well. All right, all these tools, I mean, you see here PyPSA Europe, and so they're different maintainers. So just want to clarify that. Yeah, moving on. I think it's awesome that you're all here. I think we are on a, like, we bet on the right horse. PyPSA is, I think, at the moment, like one of the most popular open energy planning tools, energy system planning tools. And yeah, I think that GitHub stars that you can see here, they're indicating the kind of popularity in that field. And yeah, I think that shows that there is something. I think is, for me personally, it's just great software, great documented, and that's why I start using it. And I think more exciting projects are coming. Okay, so PyPSA-Earth, what the heck is it? I mean, it's basically like PyPSA Europe. We just, like, for people who don't know PyPSA Europe, you have JS inputs, you have non-JS inputs. Then you sometimes create data from this highly resolved data. Sometimes you add demand data, and then you bunch that, like mix that together. You have the data fusion modification part, and then at the end, when the data is ready, like you basically insert it in the problem formulator, which is PyPSA. Then you have your optimization problem, you solve it, and then you get cool pictures out and stats. And yeah, like basically, I mean, just to show you that it works actually in Africa, we recently shared our preprint, and we were optimizing a 2020 case and a 2060 case in Nigeria. So it's up and running, and it practically works for every country in Africa, and probably yeah, also in other parts in the world. Like that's what we're testing at the moment, and mostly it's like a positive trial. But that shows you can just use PyPSA-Earth for any kind of country or set of countries. You know, you can look at whole Europe, whole Africa. Then yeah, but there's also some new stuff. So basically, it's not just a copy of PyPSA-Europe. We obviously needed different data, so there are a lot of data integrations. Basically, our main, I think, cool thing is that OpenStreetGrid, like the OpenStreetMap grid, and we also extract generators there. We have global protected areas. Everything is global land cover. Global load data and hourly resolution, some parameter updates, and there's certainly also improvements necessary, so we can work on that. But yeah, the validation was quite nice in the Africa case, and you can read more on that preprint on that. So there are also new functionalities. If something wasn't generalized for the Earth, we generalized it a little bit. We have a new clustering part, so you can not just use that Voronoi zones, but also administrative zones if that is necessary. Similar to PyPSA-Europe SEC, in the gas grid, we have some kind of augmented lines. So you can just create a network infrastructure if it's not already super meshed. And yeah, like the new testing validation procedure and also some illustration that we just share, yeah, as basic thing. Yeah, and then there's a big validation that happened for Africa, and now we are hopefully working on other parts around Africa as well. I mean, it's basically what we're doing now, and yeah, how to be part of the team. So yeah, get really informed, you know, check out the preprints, check out YouTube, GitHub issues, PRs. I mean, it's really for everyone who wants to use this kind of tools. Yeah, then the next part is using it. So apply the tools, you know, have a goal in mind, pick a small study, big study, play around with it. Then you can, for example, you know, think about new methods, technology, performance increases, new validations, or, you know, even create a new package that is necessary, for example, for certain data extractions. And then you can always reach out to find out how you can actually contribute, because that's really in the PyPSA-Earth scope. We really want to work together on this. We don't want to just create the perfect world with a small team in Europe. But yeah, like we try to grow as a community and get all the cool stuff in, such that national models are not so necessary anymore. And you can represent your country in that model. Okay, then I'm just handing over now to Katja.
Thanks, Max. And we are trying to apply PyPSA-Earth procedures for Central Asia. Central Asia is located in the middle of the whole Eurasia. That is a region with currently it's heavily dependent on fossil fuels, but that is also a region which is very open to the world, and the energy transition here is emerging. But there is a huge knowledge gap, actually, because the whole consolidated experience of energy systems operation indeed is based on fossil fuel, on centralized, highly centralized systems, and so on. And there's still huge deficit in modeling which account for renewable technologies and for the centralized generation. And next, please, Max. Yes, and there is also problem with the data, because I cannot say that we do not have data at all, but we do not have curated data sets. You can have fragments of high quality, and then something not so high quality, and then nothing at all. So we have pieces which can be used for validation, but we do not have the whole data set. So that is a problem when you are trying to build the model from scratch, and to be honest, just to prepare data for it. And that is point where PyPSA-Earth approach was very well useful. So what we have done, we have fulfilled PyPSA-Earth data workflow. Then we have established validation procedure, and we have compared our PyPSA-Earth derived datasets with the data which we had. So it has worked, and we can be sure that our model is more or less adequate. And actually, the model run has taken quite short. And what was important, it was that when we had troubles, we every moment had support. We was able to refer for help and for advice, and the fixes which we have done have taken into account not only our needs, but also global perspective. So we very well hope that our improvements will last, and that is a very pleasant feeling, to be honest. And last but not least, we can be sure that we are in touch in global, in state of the art, both in research and in development. And it makes your life easier. And last but not least, it is just very funny.
Thanks, Katja. Yeah, I mean, like, that's basically it. Yeah, so you can change the world. You can actually contribute to something, beyond your own model in your region. As Katja mentioned, like, we fixed something, and that actually addressed a lot of points around the world. And yeah, would be great if someone is interested trying to find out how to represent a country in PyPSA-Earth. And we can also, create interfaces to represent accurate data for that country and all that stuff. All right, I'm just stopping here. I think we're a little bit over time. Sorry.
Over time, but as you have been two speakers, still very well done. There is one question in the chat, and anybody else who has a question could also raise their hand. And now, the question being, for Central Asia, has their amazing wind and solar, will you also explore the hydrogen that could be derived from exports in that region?
We will be happy. Actually, we have just run model and obtained the first results. And yes, I think about hydrogen, that is a very good topic. And I think it has been discussed. So discussion has started, and our modeling could be a good support for this discussion and for taking decisions in future, I hope.
Okay, thank you. And we have one more question from Robbie.
Yeah, hello. Can you talk about the requirements to entry for using PyPSA? One of the other modeling projects in the space suggested that a knowledge of Python, a knowledge of the command line, and a knowledge of energy system modeling was not necessary. And I rather think that's not true. So could you make a comment on the requirements to entry?
Yeah, like, I think the instructions so they improved just now, like, we updated the documentations, but I think if they're clear, like, anyone without knowledge can start, and then, yeah, like, you find your way through. Often the setup is sometimes difficult, but there's a great tool called Google, and that usually really helps you a lot. And you can ask Google everything regarding code. Someone had the same problem before, and yeah, you find a solution. And this is, like, relatively, I think, in less than a day, you have, for example, one model run. if everything runs smoothly and the CI is stable.
Okay, thank you. We have two more questions. Because of limited time, we're going to take one question now from Alex. And Nicholas, if you can take a note of your question, there will be more room for Q&A after all the talks. Or put it in the chat. Great.
Put it in the chat and the speakers can answer it then directly.
Yes, Alex.
That's awesome. Thank you, guys. This is really impressive. I wonder if you guys have any team in Northern Europe, especially in Denmark. Can you hear me?
Is it sorry, what's the question? We're still in the Q&A?
Yeah. So you mentioned that
I think
you would need representatives
exactly.
for countries.
I mean, so the European, PyPSA Europe is probably most suited for that case. We really try to focus on countries outside of Europe, and then Tom and the colleagues, they focus in Europe, on the European continent, and they have definitely better and more validated data for that scope.
Right.
Yeah, so you can definitely reach out. PyPSA Europe can be used in the same way.
And we have a team at Aarhus University that uses the tools intensively with a focus on Denmark. So Tim Pedersen will be speaking later on that.
Okay, great to hear. Thanks.
Okay, thank you, Max and Katie. We now move to the next speaker, Samuel Matthew Dumlao from Kyoto University. Samuel recently received his doctoral degree from the Graduate School of Energy Science and focused on the impact of solar PV on the electricity grid in the Kyushu region in Japan. And currently he is affiliated with the Center of Southeast Asian Studies at Kyoto University and compares the energy transition in the Philippines and Japan, mainly on the potential for decommissioning of coal power plants. And today, Samuel will talk about weather-related risk of replacing coal power plants with solar PV. And we welcome very much Samuel.
Hi, good afternoon. Let me share my screen. I think you have to turn off your screen. Thank you. Okay, so good afternoon. I'm glad to be here. So to be part of the first PyPSA user group meeting. So most of the information in this presentation is the fruits of my research work when I was doing my doctoral studies with my supervisor, Professor Ishihara. He introduced me to PyPSA. I am very grateful for that since it has opened me to a community of open modelers. So just to give a brief background about Japan and its energy system. Unlike the European countries, being an island nation, Japan cannot trade electricity with its neighboring countries. So within Japan, the governance of the electricity system is divided into 10 independent power companies, so as you can see in this figure. Now, 9 of the electric power companies are actively engaging in electricity trade. Okinawa is not part of the map since it does not have any connection with the other islands of Japan. So as you can see here, it's noticeable that most of the transmission is sent to the center of the main island where Osaka, Nagoya, and Tokyo are located. So these are the population dense cities. So overall, Japan has a total annual energy demand of around 880 terawatt-hour. In July 2018, the country published its fifth strategic energy plan, where solar has a 7% share. As of 2019, this was already achieved, so they increased this further to 14% in the updated strategic energy plan. Now, Japan's solar capacity has been growing steadily since 2012, mainly driven by the FIT program. It has then transitioned to the feed-in premium in 2020. At the current rate, it could reach the 108 gigawatt capacity by 2030, which will satisfy the 14% target. So as you can see in the table, Tokyo, Chubu, and Kyushu leads the installed capacity. However, Tokyo and Chubu, these are population-dense areas, but Kyushu is a little bit less populated. Okay, so from there, I set my attention to the Kyushu region because mainly the region has higher solar irradiation relative to the country, and the land is also cheaper. So it's more suited for PV installation. So the penetration rate of solar PV has been increasing significantly in this region. At the same time, about already 25% of the production is already from renewable energy as of financial year 2020. Therefore, it satisfied most of the target, the previous target, and most likely it could easily achieve the new target for 2030. However, this has led to curtailment problems as early as October 2018, which prompted my study of the region. And further curtailment were seen in the spring of 2019. So curtailment is now a normal phenomenon in the region. So under those premise, we got curious if more solar PV is enough to decommission the coal power plant in the region. So, and we are mainly motivated to explore the possibility of decommissioning coal power plants since this produces the highest CO2 per kilowatt hour. And in our objective, we wanted to understand the weather-related risk of decommissioning coal power plants because we think that the PV is highly weather risky in terms of weather. So we also wanted to reveal the impact of yearly variations to the factors affecting solar generation and to show the potential of solar to reduce the coal capacity. The flow of our analysis has three major parts which start from the weather selection, followed by the generation of the synthetic energy demand, and then we generated the solar power generation. For the weather selection, we looked into the past 30 years and selected representative years based on the temperature level difference against the comfortable temperature, which we, according to some literature, is between 18 to 22 degrees. So we identified several combinations of mild, severe, and extreme winter and summer months. Oddly enough, most of the identified years happened in the past 10 years. With that, we then implemented a demand fingerprint methodology to generate synthetic energy data. So this allowed us to create demand curves based on the representative years. When we look at the data for the demand, we observed that we could cluster the demand into 5 major waveforms, which changes depending on the maximum weekly temperature and the minimum weekly temperature. We also observed that there is a correlation between temperature and minimum and maximum energy demand. So therefore, by combining the weekly fingerprint and the correlation of temperature and maximum and minimum demand, we were able to synthesize demand based on the temperature, and we were able to make the demand curves for the selected weather conditions. And then for solar, we used the PBlib library, another open source Python library. So with that, we were able to combine the synthetic demand and then the generation from solar and some other information about generation for the region, and then we used PyPSA to simulate all this scenarios. So we come up with a weather-driven scenario-based analysis. So this is one of our results. So this figure shows that the minimum coal capacity that could satisfy the demand for various combination of solar PV installed. So as you can see here, we increased the LNG quota from 10 terawatt-hour in terms of electricity, and then increase it further until 12 terawatt-hour. We started with 10 because this is the current quota of the region based on our analysis. And as you can see, we can reduce it further if we have more LNG in the grid. So to decommission the aging 3.5 gigawatt of coal capacity in the region, around 10 gigawatt of solar energy has to be added, and then 16 gigawatt of LNG quota should be added into the energy mix, which represent this part. So currently they have around 7 gigawatt, and then if we want to cut that into half, then we have to increase the capacity to these values. However, as highlighted in this figure, around 400 to 600 megawatt of standby coal capacity is necessary to account for yearly variation. So this depends on what happens per year. I think in some countries, they have to put up their coal power plants mainly to satisfy some yearly variations. In the same way, this is what we saw in the Kyushu region. So this standby capacity will be needed during winter and summer months period, particularly during January, February, August, and September in Japan. And then this figure shows the improvement brought about by a decrease in coal capacity. So we all know that coal is we use coal as a base load, and it's not compatible with solar. So if we increase LNG, then the combination of LNG and solar could reduce the solar curtailment. And this is the combination of these two as well could cut the CO2 emissions by half, but could also significantly increase the cost of power generation. So we wanted to summarize the results into this part, into this graph. So we wanted to see the levelized cost of generation, or vis-a-vis the cost, the levelized CO2 emission, how much CO2 are we producing per kilowatt hour. And as you can see here, this is the increasing solar capacity and increasing LNG quota. Currently Japan, or the region, is here. And if we increase the LNG quota, that's the easiest way to do it. But we can also increase the solar capacity. And the best way to do it is the combination of higher solar capacity and higher LNG quota. But one of our major concern is that LNG is currently so volatile. So we don't want to heavily depend on LNG. So the scenario which would be feasible might be these two other scenarios, or this part. So in conclusion, our results emphasize that solar with the aid of LNG could partially replace coal capacity, but it is not enough to phase out coal. From an economic perspective, we think that it's difficult to replace coal, but solar with LNG will have a significant impact on CO2 emission. And standby power has to be there for us to reduce the risk. And the main problem is during winter and summer. And I think for most European countries, these are also the case. So for future work, we already explored hydrogen instead of LNG, but the infrastructure needed to support this seems unachievable at the moment. So we are exploring other scenarios. I'm also interested in expanding the simulation for the entirety of Japan. Although the data are available, they are scattered and it takes some time to consolidate them. And outside this region, I'm also interested in energy system modeling for the Philippines, my home country, and its neighboring countries in the Southeast Asia. So feel free to contact me for possible collaboration. That ends my presentation. Thank you very much.
From the chat, one quick one. Not sure if you already answered this. If you plan to share the code about weather profile generation.
The weather profile generation, I think it's available in my GitHub. So it's
okay, so
the fingerprinting is available for the code for that. But it heavily depends on having hourly data. So I can do it for Japan, but I cannot do it for the Philippines because we don't have the hourly data for the fingerprint. So if your country has that hourly data, then yes, you can utilize the same code.
Okay. Question from Tom.
Yeah, I was just wondering, I remember when I was in Japan, the Kyushu grid operator was saying that because of the system inertia, that they couldn't have too much PV because Kyushu is a bit isolated from the rest of the grid. Do they still say this? Is it still used as an excuse? Because I think you could probably just use the gas generators in synchronous condenser mode and you'd be able to provide some inertia that way.
I think the major concern is they don't want to rely heavily on gas.
The grid operator?
The grid operators, yes.
Because they don't want to deal with the gas, or what's the reasons they say for that?
Because usually they need the gas during winter, and during winter, Japan and Korea, they fight about the gas price, the LNG gas price.
Okay.
So during that time, then it becomes very, very expensive. So when I proposed that they increase this LNG quota, my supervisor said that this might be difficult for the operators because they think about the cost during winter. That's why we wanted to explore hydrogen in the future.
And there are also two questions from Barry McMullen.
Sorry, Samuel, thanks a million. You kind of answered that you do intend to look at hydrogen as replacement for LNG. The main question really I had is whether you try to factor in the upstream emissions from LNG, so that there is obviously concern about methane, especially from LNG systems. So that wouldn't be territorial emissions necessarily for you, but it would be associated with deployment of more LNG. So have you thought about that?
Can you repeat the question? Sorry.
Sorry, have you thought about upstream emissions from LNG? So when LNG is extracted, liquefied, transported, there are expected to be some emissions of methane associated with that, but that doesn't occur in your territory. So in international terms, you can say it's not your problem, but on the other hand, it's arising from your consumption. So is it something you've thought about?
Right now, we only consider during the production. So CO2 emission during the production of electricity. So no, we did not consider it, but I think that is something that we should also look into. Okay, it's just arguably it may undermine the attraction of LNG in terms of decarbonization. It's not quite as good as it appears. Okay, thanks. Thank you for that question.
Thank you very much. Also, Matthew, for the presentation, I think there's one or two more questions in the chat if you want to answer them there. And regarding the slides, we will share all the slides that the presenters make available. So this will be kind of a case-by-case basis. I'm not sure, Matthew, if you plan to share these slides or if you use them in other formats.
I'll upload. I'll share it through the program.
Okay, yeah, we'll have those consolidated then after the meeting for everyone. Okay, we now come to our third talk. Georg Thomaßen from the Joint Research Center at the European Commission. Georg is a scientific officer there, and the JRC is the research division tasked with synthesizing data and research for the policy process at the European Commission. For example, he is consulting for the Directorate General for Energy and for Acer on different aspects of electricity market design. And before his current position, he was also a policy analyst and modeler at Agora Energiewende. Yeah, welcome, Georg. We're really excited to have you here.
Yeah, thank you very much.
Multi-annual capacity optimization.
Yeah, thank you very much. And again, I would need to share my screen. Perfect. So I hope everyone is seeing the presentation now. Okay, I will just continue and assume that everyone does. So let me talk a little bit about the context of the work that I'm presenting here. So generally, some of you might know there is this European Resource Adequacy Assessment that ENTSO-E performs every year, which evaluates how much capacity we have in the European system, whether there is a danger of shortfalls in the near future. And JRC supports ACER in the monitoring of progress of the implementation, because there is a time frame. I think in 2024, there needs to be the implementation of the full methodology, which is quite challenging, but we will get into this. And until then, there is a stepwise implementation, and we give feedback on what ENTSO-E is proposing to do, how they model different aspects of this assessment, and then ENTSO-E, then ACER takes this into consideration, communicates this to ENTSO-E basically. One aspect is the so-called economic viability assessment, which is supposed to assess what level of market-based investments can be expected. So we have the national estimates, what TSO thinks, what capacity is there in the system in, for example, 2025. But then this needs to be assessed. If then turns out that half your capacity is not profitable, you might want to reassess whether you can assume that the system is reliable. Or on the other hand, if there is a lot of capacity, a lot of investments that could be made that are profitable, then maybe you still don't need a capacity remuneration mechanism to enhance your supply security, because the market could take care of it. The challenge of this assessment is that it is supposed to cover the whole data set, which is 35 weather years, and also the full lifetime of the asset. So everyone who is familiar with investment modeling can see that this is quite a data challenge. 35 weather years is, I think, 306,600 hours. And we have all market zones in Europe. And to put this into a capacity expansion model, which performs capacity expansion in one run, is quite a challenge. On the other hand, we have to be very careful with reduction, because there is a high sensitivity required. If we have a loss of load expectation of 10, and this is kind of the maximum we're seeing, unless we have some weird extreme cases, then this means 10 hours of 8,760 hours on an annual average is roughly 0.1% of all hours. So if we miss some of these hours, our assessment will already be wrong, and we will not have the right capacity level or not the right loss of load expectation. Therefore, we looked into alternative ways how this could be done. At the moment, ENTSO-E is doing this conventional capacity expansion method where they optimize it in 1 year, they cluster years. But we wanted to explore an alternative method and use PyPSA for this. Working name at the moment is PyPSA-EVA. And this model is using an iterative capacity expansion approach which adds or removes capacities based on whether they're profitable in the market or not. And the scope supports all zones that are covered in ERA, so the European system, basically all ENTSO-E zones. And the nice thing about this capacity expansion process is that generally we cannot only use this for such a case where we have a lot of input data, but we can also use it for all kinds of assessments where we, for example, want to model several market sessions in sequence. But then we can take all the revenues into consideration, just an investment, and then basically to the next iteration. So this is a short description how we do this. First, we initialize the model. Then we run all weather years and all scenario years. So 35 weather years times 30 scenario years, which comes roughly into 1,000 model runs for one iteration. And generally, we can, of course, extend this or reduce the set. This is completely possible. And then we evaluate the revenues and the costs of each technology at each node. We apply then a scaling factor. So if your power plant or the technology in one country has 50% more revenues than cost, then this would equal to a certain factor that you increase capacity. If you have less revenue than your cost, then you reduce capacity according to a certain factor, and then you start the same thing. You start the whole process basically in the beginning and do it for as long until you reach that stable point where revenues equal costs. This is the overview of the computation routine. I don't want to go into detail of all of these, but you can see that it's kind of like a circle process. Here you have the pre-optimization, you build the model, then you solve the rolling horizon, you evaluate, and then you go back and do the same thing anew. And I think that's basically all to take away from this graph. And then lastly, I just want to show because it always feels really nice and you see that the numbers are converging, which you can see on the right. So at first we have 100%, everything is indicated as normalized to its initial capacity, and then you can see how the technologies compete against each other. We see how lignite is phased out, and hard coal is also very much reduced, whereas we have more investment in OCTG. And as I already mentioned, you can kind of have a modular approach to these kind of models. So you can add different components. For example, a capacity market can be added that can be applied after the runs. Of course, in the model, we want to also expand the representation. We want to include balancing markets, ORDCs, a bit further down the line, flow-based market coupling. For this, we will probably rely on PyPSA-EUR, and of course, more storage that is more technologies that is included in economic viability assessments, such as renewables and storage. And that's basically it from my side already. Thank you very much for the attention.
Okay, thank you very much, Georg. There's already one question in the chat from Koen. If you want to pose it.
Yeah, sure. I was just wondering, this looks really interesting. So is the code for PyPSA-EVA open source or going to be open source? Because I would be very interested in looking at it.
That's a good question for which I cannot have an answer at the moment. So I would like to open this up, but of course at the Commission we are kind of let's say it's not just our own. We don't have the freedom to simply open it up. We need to check this with the hierarchy, and then if they say it is fine to open it up, I would be very much in favor of it. I was even thinking about having something like an European. So I mean, there are two things: the method. I think this could be easier to open up, or then the full assessment. Ideally, it would be the full assessment, but this will still needs to be seen how much we can open up.
Thank you.
Georg, did you try comparing it to some time series reduction? I mean, you're doing the iterative because of the time, I guess. Did you try comparing it with a sort of reduction that focuses on the difficult hours or something?
Not yet. So this is something that is still in work at the moment. So this is something we will. I mean, if you want, NSOE is doing that because they're doing a time series reduction, but of course they're not exploring every method there is. First, I've been trying to actually solve this issue through a time series reduction, and I ran into quite a lot of challenges because I think to do this, generally it is possible to get good results, but you still need a lot of computation capacity. So you would still be talking about investment runs with at least 3 to 5 years of complete data. Of course, if you then manage to reduce your annual data a bit, you could actually make it feasible potentially. But we have not looked into it at this detail yet.
We'll also be looking at some decomposition algorithms to separate the years of it. Sorry, I see a question from Koen. I know he has his hand up again.
Sure. I also just want to ask as a quick follow-up, like, is the kind of sub-problem, like each iteration, is that actually a linear optimization problem, or is there also, like, is this a more complicated optimization? I don't think I quite caught that.
No, it's a linear optimization problem, but the nice thing about the approach is you could even do it with unit commitment. Of course, then you would kind of have to find a way to assess what investments you see, because you cannot simply expand a block to make it have, or at least I'm not sure that you can do that, just expand the capacity. Normally you would add another block and not just have a block that is larger. And but generally, this is, I would say, this is maybe one advantage of the method, is that you are not limited to making it linear, the overall investment problem, but you can also, for example, have, if you want, a nodal system, and then you can have redispatch, and you can calculate the revenues for both market sessions, and then based on two, you can adjust your capacities basically, and these things. I mean, there are a lot of different, or you can even, for example, very relevant in the current time, you could even implement something as is proposed on EU level with regard to the inframarginal, the reduction of the inframarginal rents, that you limit rents for some technologies which you would not be able to do in a simple capacity expansion model. So it allows for a bit more, let's say, interventions in the market that you could also assess in this context.
Okay, cool. Thanks. That answers the question.
Great. Thank you very much for these great questions. I think we have a couple more in the chat if you want to answer them there. And we will now move to the next presenter. We have Pawel Czyzak from Ember. Pawel is a senior analyst with Ember, a London-based climate think tank, and currently focusing on the acceleration of wind and solar deployment in Europe through open data and open modeling. And Pawel also holds a PhD from Warsaw School of Economics on the impacts of energy risk on Polish enterprises. Quite an interesting topic, probably. But he will be presenting today on utilizing PyPSA to advance national energy policies in the UK and Poland. So welcome, Pawel.
Thank you, Chris. Let me share my screen. Just a side note, my PhD defense is next Friday, so I can't really state my title yet, but hopefully no surprises there. I hope you can see this. Let me just yeah. So I thought, because there's so many very interesting modeling exercises and modeling work done across our contributors today. But I thought I'd talk a bit less about the modeling we're doing itself, but talk about a bit more about the communication and the outreach, the impact we're trying to generate through the modeling and analysis work. And I think that's in fact the thing that Ember does best, which is taking some of these analytical tools and generating some outreach among policymakers with those. So just for context, Ember, we're an NGO, a think tank based in London and focused specifically on the power sector. And I think a big chunk of our work is around open data and making global data on energy, electricity accessible. And I'll start with two examples. One will be the UK. We've done some work recently on modeling a 2030 scenarios for the UK, which was used by the Labour Party as a sort of a basis of their new strategy, let's say. The Labour Party is the main opposition party for those based outside of the UK. And I think the modeling itself maybe isn't very extremely exciting because it's quite a simple PyPSA implementation, but I think the way we've been able to feed it into the politics is quite interesting and stirring kind of a debate around getting the UK quicker off gas than initially planned. And the second example is from Poland. Through my previous work in Poland, we've launched a few studies around the coal exit in Poland and around transitioning Poland from coal to some other energy sources, and I think that achieved quite a lot of impact as well. For example, most of the phase out coal exit dates we've proposed for specific coal generating plants were actually adopted through the just transition plans. Local just transition plans in a few regions in Poland, so that quite a lot of policy actually changed through those different studies. And I just wanted to touch on how maybe you could use some of the experience we had with this policy and think tank work in your in generating some outreach from the great work you're doing in the modeling. So just a few areas I'll touch on. One is the timing. So one issue we've been seeing is that modeling exercises take a lot of time, sometimes even running a year or more, multiple years for Horizon projects, for example. And of course, for research academia, that is fine. But for policy impact, we're trying to look at very quick turnarounds, maybe 1 to 3 months. And one of the examples we did is the Polish work last year that actually targeted specific policy events. So, for example, a discussion on market restructuring, a bill, wind law was being amended, or the discussions were starting around that. Then we targeted a moment when energy utilities were upgrading tariffs. And I think all of these made it easier to communicate the results and to feed them into the media during a time when it's actually relevant. And another thing I think that worked quite well in this case was that we've been building the PyPSA model gradually. So we started with quite a simple sort of unit by unit coal phase out scenario, but we then expanded through the work of spatial analysis and sort of mapping all the renewables that we could build into a more complex res expansion model. And then finally we went on to grid modeling, modeling the tariffs on all the tariff components. So I think that's quite an interesting way of launching a study as well, when you're building, instead of building the whole PyPSA, a very architecturally complex model, all at once, you could actually make it more modular and launch it in modules. And then just a note on transparency. Of course, this is in our PyPSA world, this is the recommended and, well, sort of base approach, but it's not the case in even among NGOs, especially not among governments. So of course, open source and open code, open data is what we're fighting for. But I also wanted to mention a bottom-up approach. In many national situations, a top-down model is not very easy to communicate or to actually defend, because for example, we are seeing global consultancies coming into a country like Poland and saying, okay, you need to do this and that, but they're if they're coming from for example, a global model, like, I don't know, scaling down an IEA model, it obviously doesn't address some of the regional issues we're having, or the unit by unit technical constraints, etc. So one thing I would like to underline for national work, I think, is the bottom-up approach, and actually talking to some people in a specific country and trying to map the specific generating units, the grid infrastructure, etc. And then, of course, we have the different levels of sharing your outputs through, I think, describing the methodology, then through sharing your inputs, and then, of course, up to sharing your whole source code, which is, again, not the case in many studies. And then finally, we have the communication. And that is, of course, a big topic in general, and maybe not so relevant for all academics, but I think in general, it's just nice to know that your work is actually working in the real world. And for example, you can feed it to policymakers who are still using like 1990s models and advance national policies. And for that, we've been using a few methods. For example, we're trying to aim for a very big and relatable number. So from a huge modeling study that, of course, has tons of outputs, we try to pick a number that is very relevant or very easy to understand, like the UK can get to 1% fossil fuel use, or a government can save X billions of money, or, for example, and this is working very well even with tabloids. But one other approach is to actually say each UK citizen can save 500 pounds a year. We've done the same in Poland, and that actually can get you into the large scale media that can then get you into the policymakers world, and into campaigns, of course, as well. And similarly, the visualization of data, I liked Max's comment on some new tools being introduced for actually visualizing PyPSA data, because the outputs there's a lot of them, and it's not that easy if you don't have some Python visualization skills. It's not that easy to actually make something actionable from them. And then there's the last thing is addressing some of the concerns about our modeling and our work, and in general res-based systems. I think this is an example from National Grid from the UK, where they actually show a very step-by-step explanation of how highly renewables-based system would work day by day, hour by hour, in different weather situations. Just I think a nice inspiration if we want to actually defend our numbers. So yes, just some key messages. If you want to get with your results into the policy world, I think the timing is very important. Targeting some specific policy events. Of course, transparency, we're fighting for that. I would stress visualization and communication, and we are always happy to help with that. If you have an academic project, for example, running and you want to spread the word, we're always happy to support that. And yeah, that's it from me. Thanks.
Great, thank you, Pawel, for these insights on modeling for policy impact. We have a question in the chat from Alexander and then a raised hand from Tom.
Yeah, sure. Thanks a lot. This was super interesting and relevant. I was just wondering if the two impact examples that you talked about, whether they just picked up the policy papers that you've put out, or whether they were actually interested and there was some exchange and follow-up research.
Yeah, I didn't really expand much on that, but yes, in terms of the UK, we've actually had a lot of exchange with a lot of different stakeholders, including the national grid, so the TSO, some utilities, politicians. So it was quite a, I would say we've been quite overwhelmed by the number of people that actually approach us from institutions that are normally not very open to discussion. And normally the way we sort of communicate the work is not only through just putting a paper out. We of course target media and talk to journalists. We usually send it to specific policymakers in ministries and institutions, European Commission. We often partner with different NGOs or different think tanks too. So yeah, there's, I think, a whole palette of getting your word out.
May I?
Yes, please.
Thanks for the great presentation. It's good to see also other think tanks in this group. I think I have a comment and a question. The comment is actually, I've been thinking about this with regards to data visualization. I think, let's say, a request and what I read into your presentation, the map that is generated as an output from PyPSA-EUR typically, although very beautiful for policymakers, it can be a bit overwhelming. And I think more, you know, stacked bar charts, stacked area charts, or stacked columns, simpler or even pie charts can be quite powerful in their simplicity in conveying a message. And let's say that putting it out there for the community, that it might be, I think it would be a worthwhile endeavor to put this in the workflow for PyPSA-EUR. So that's the comment. In the question, I'm quite intrigued. You went, from what I understand, you basically decided to build your own model for the UK based on PyPSA, the framework, but PyPSA-EUR, of course, does include the UK as well. What were the factors that led you down, well, not choosing PyPSA-EUR?
Yeah, I think I saw that question on the chat as well. So it's just we needed something very quick and very simple. We had a 1 month turnaround, and I find PyPSA-EUR a bit difficult if you need to do big changes in it. So have very specifically the latest generating units and the latest demand, and you know, very up-to-date assumptions from a strategy that was published a week ago or something like that. So I've personally struggled a bit with adapting it to a very dynamic environment. So we ended up building a very, very simple, just a raw model with even no capacity expansion, but just to sort of run quickly and see that it actually balances itself. So that's a hurdle I had with PyPSA-EUR a bit, that it's a bit tricky to do a very bottom-up approach with it.
All right, thank you very much for the comment and questions. I think there's more questions in the chat to answer. And we're now staying with Thomas Kouroughli from Agora Energiewende. Thomas is a policy officer at Agora, which is Germany's premier think tank for energy transition questions. And he will be giving his presentation, his talk today on the link between open source model and energy policy. So the floor is yours, Thomas.
There we go. So thank you for giving me the time and to present here. A bit like Ember, I'm going to take a little bit of a different approach. I don't want to focus so much on modeling results, but maybe just to communicate more as a user, as an NGO, a think tank, and where our primary goal is not the modeling itself, but rather the policy impact, how we think about open source modeling in our work. And maybe to start with, just a short word on why we think open source modeling is important for the energy transition. And basically it boils down to this. What we've seen, and I'm sure a lot of you are familiar with this problem, is that everyone can essentially pick their model. Every kind of interest group can pick their model that fits their own narrative the best. And when you have black box models, it's very difficult for policymakers to discern what is credible and what is not. So the gas industry will have their favorite people and favorite model that says that there's hydrogen everywhere and that's the only way. And the nuclear industry will have a different answer, and so on. And so the question of open source modeling for us is really about helping policymakers discern what is a good quality study, and basically leading to better policy outcomes for the energy transition. Okay. So just a little bit of background about Agora before I go in detail. So we just had our 10-year anniversary. We primarily were a German energy transition think tank, but as the energy transitions sort of grown and evolved, we saw the need to expand in our scope in terms of sectors. So we have Verkehrswende, which addresses transport, and we have industry for the industrial sectors, and now Agra, looking at the agricultural transition. And meanwhile, also in terms of geographical scope, we've expanded to basically the top 20 countries that we see as key for the energy transition. And fundamentally what we're doing is working towards a carbon neutral economy globally by 2050. So until about 2 years ago, all the studies we conducted were that required energy system modeling were used. We hired consultants that use black box models, basically, and especially in the international context, especially in the global south, what we saw is, first of all, there was a lack of consultants, local consultants. So we were often driven through need to go back to European consultants who fundamentally didn't have enough expertise from our perspective on the local situation. And what we did is we kept, I mean, the studies that we publish are, even if you look at this latest Ember study, they're usually addressing the same questions. How do you integrate more renewables? How do you reach your targets? What are the questions around flexibilizing thermal power plants? Does that help? What's the renewable potential in a country? Now, of course, we have more questions around hydrogen and industry decarbonization, but fundamentally the questions are the same. They're just in different geographies. And so what we understood is that it might be worth actually building capacity in the country with open source models, and building capacity within Agora to address these questions, working with our local partners for that local expertise. And so that's why fundamentally we got into open source modeling and using PyPSA. So to give you one example of a study that we just conducted, it's not been published yet, but we built using the PyPSA framework, we built we call it Power Plus model, which is a high temporal resolution model. It's 5 nodes, which represent the this is in Thailand, which represent the control regions in Thailand, and it has a transport sector, and it has a kind of, let's say, middle, yeah, like mid to high resolution in the industry sector representation, and for low heat and low, medium heat and high heat, and for synthetic fuels. So we did this in the context of a government-to-government program between Thailand and Germany. And we did it in close collaboration with EGAT, which is the state-owned power company, and with also with the Ministry of Energy. So we had, let's say, we gained credibility and institutional. We were institutionalized through this government-to-government project, but we also the important aspect of this was that we used an open source model. We used the argument about open source to build trust with the stakeholders. So we told them whatever assumptions that we're making, you can see them, you can see all of the code for yourself. And not only that, but we are actively training stakeholders in Thailand to use this model, and we're handing over the model to them so that they can use it in the future. So we're capacity building, but also we're using the open source logic to actually build trust and make our what are typically conservative institutions in terms of trying new things, making them comfortable with cost optimization, with high resolution models, and with sector coupled models. We plan to do this in Vietnam, in Indonesia, and the Philippines as well, and to essentially take a similar approach as we did in Thailand. And I heard already some people in this room talking about their interest in the region, and we'd be very happy to collaborate with you on these questions. Okay, just to close, I kind of I call it my wish list a little bit, but what we see as, again, as a think tank, non-academic, and also operating with and communicating with institutions and people who are not necessarily coders, are not necessarily modelers. They're more comfortable with, let's say, I mean, especially in the Southeast Asia region, programs like LEAP, right? They haven't done that much cost optimization. The question is, how do we, going back to this first point that I made, why open source modeling is important, and also we know why high resolution temporal and geographical models are important in these renewable systems of the future. How do we get people in those institutions to use them, to feel comfortable with them? Yeah, so there's a couple points there that I wanted to make. I think there has already been a lot of work that I've seen from different people, again, in this room, about producing training materials and videos. We ourselves are also producing training materials. And as I said, we're actually going to run some workshops in the region with certain stakeholders. Nevertheless, I think there's a kind of gap still, and it's difficult without having some level of Python knowledge and particularly a certain kind of commitment, to be honest, because actually, in my personal experience, the hardest thing about using Python is actually installing Python on your machine and having your environment working when you've never done that before. And so, should you choose Anaconda or whatever else? This is one point I think that we need to really think about who our target audience is here, and how do we make it as frictionless as possible for them to access these tools. And related to that is an idea that's been floated and that we are very interested in, and we're looking for collaborators on, is to build a GUI, a graphical user interface. So again, there is an audience of people, there are users who, if we build them a GUI, it will be much easier to convince them to use this tool, just like Leap. And so, as I say, if this is something that you find interesting, we'd love to collaborate with you on it, and potentially do a joint application for funding. The other thing, the other question is, you cannot do everything yourself. So even Agora, for example, fundamentally, we do not have the resources to do every modeling study. And, there's a certain pace at which you need to go in politics, which means that sometimes it's just easier to find a consultant to do the work. There are not many consultants who are willing, because they see it as their IP, who are actually operating in an open source fashion. And so again, I'm kind of making this call out and saying, if you see yourself, essentially what we need is a team of people and consultants who are willing to use open source, in my perspective, obviously, ideally PyPSA, to do these kind of work. So with some reputation, with technical expertise and know-how, but willing to do these studies with NGOs, with whatever relevant party, completely in an open source way, following the open source logic. And finally, let me just finish this one point. Co-optimization of the power sector with industry is becoming a much bigger question with regards to hydrogen, how much hydrogen versus how much electricity to decarbonize industry, for example. And here I think going to governments and telling them, actually, you can use this model to do this is kind of a good way in. Yeah, that's everything for my comments. Thank you.
All right, great. Thank you very much, Tom. We have a question in chat on the training materials from Katie.
Yes, Tom, thank you so much for a very insightful presentation. I have a rather technical methodological question. When you mention about learning materials and videos in particular, do you mean technical details, how to install Python and so on, or rather high-level presentation about how to, why open modeling can be useful for you? Which real-world problem can be addressed?
I think both.
Okay, I see.
That's the answer.
See, the better.
Yeah, I mean, definitely, of course, the logic of why and the advantages of why, absolutely, we need to communicate those more. I mean, this is also my job, right? But particularly, honestly, really like step-by-step guides. Like, there's a lot on GitHub, for example. But GitHub itself, you have to know what GitHub is. So if you've never done programming in your life,
yes,
you're not going to look for things on GitHub. So, we just have to put it in the right place and in the right format so that it's really accessible to non-coders and non-experts. Yeah. Thank you.
Thank you.
All right. Thanks, Tom. This is really a group to increase the policy impact of modeling. That's really important to keep it at it. And yeah, we hope that you're successful in your call to develop a GUI for PyPSA. This would certainly be useful for a community as an add-on. Our next speaker is Aleksander Grochowicz from University of Oslo. Aleksander is a PhD candidate at the Department of Mathematics and Technology Systems, and his research focuses on spatial and temporal uncertainty in energy systems. And today, Aleksander will give his lightning talk on intersecting near-optimal spaces for more resilience against weather variability. And we welcome you very much, Aleksander.
Yeah, thanks for the kind introduction. I hope you can see my screen now and the presentation as well. Perfect. I'm going to present some recent work that I've done with Koen, that's also here actually, and then my supervisors Fred Espenbent and Marianne Zeiringer from the University of Oslo. What I'm going to try to cover in those 10 minutes is to kind of give you a brief introduction to the work we've done, the motivation, what we've done, and what we're hopefully able to show. What I'm not able to cover, the preprint will hopefully be able to answer you. And if you want to dig a bit deeper into the code, there's a GitHub repository, and at least the people here, they know how to use GitHub. All right, let me start with the motivation. So already Samuel and Georg, they've already talked about weather uncertainty and how that plays out for especially renewable systems. And it's been shown in the literature already several times that this is important, and it has a huge impact also on the system design. So what we've done is we've run PyPSA-Ger with a 100% emission reduction scenario. We generated data for 1980 through 2020, and these, all these different bars, they show you the optimal costs of a system for that given weather year. And you can see already that not only are the bars at different levels, so the optimal system costs, they vary quite a lot, especially if you look at the 80s and then 2020, which is a lot cheaper, but also do the different technology shares. They vary throughout these different solutions. So even just saying, well, we're just going to build more for the worst years, it doesn't seem like the optimal path to go. And then kind of to bring in the second half of what we've done is our near optimal solutions. So there's been quite some development in this area. It's become very popular to use those. I've seen at least 2 people here who've done this before. So Fabian, for instance, and also Tim, who's going to present right after me. But the idea is to, instead of just focusing on one solution, you relax the cost optimality to get more options for this. So what we've done is, instead of just looking at the cost optimum, we say, well, if we deviate from a cost optimum by 5%, that's for us a near optimal solution, as long as it's feasible. And instead of a point, you can get one of these polygons, or in higher dimensions than polytopes, for different scenarios. So each weather year in our situation would then give you one of these different spaces. And the idea is to find something that actually works for all the different years with this. Ideally, there is an overlap, some sort of intersection that shows you solutions that are feasible and good enough for all the different years. And this is what we're trying to find. And this is, in our case, what we would call a kind of weather resilient or robust solution. And then what we've done is, as I mentioned, we used PyPSA-Ger for this, and we extended the data set that's underlying it. Although I think to some extent this is also now implemented in the current version, that we have hydro data from 1980 till 2020. We have ERA 5 reanalysis. I mean, we haven't done anything to it, but just ran AtLight on it. And we also generated synthetic demand data for 1980 till 2020, just to really get the variability for the different years out. And to have some sort of consistency so that you can actually compare all of this. So we've implemented some additional functions and functionalities to it. So what we were able to do is, well, run all of those different years in parallel and be able to compare them, but also just to take the entire data set and run a 41-year optimization. And since the optima are kind of the starting point to get the near optimal space, we then also implemented a workflow on describing and approximating these near optimal spaces, and then eventually using those to really get these robust solutions which lie in this intersection that I'm talking about, but also trying to really get networks out of those that are feasible and that actually work and are resilient to all those different weather years. And just because the preprint is quite heavy on the methodology, we were focusing on that because, in fact, this is something you could also use for different scenarios, for different uncertainties. So it's not only applicable for weather uncertainty, but basically these are just solutions that work under different scenarios. And our motivation here to kind of get as much robustness as we can is to look at solutions that are kind of very central within this intersection so that you can kind of move them around and still remain feasible. Whereas usually the optimal solutions lie at the boundaries of the feasible spaces. Let me show you some results just to guide you through this plot. There's a lot going on, but basically what you can see here is these are different projections on investment technologies. So always on the y-axis, you can see the monetary value of investments into onshore wind, and on the x-axis you see different other technologies. So each of these blue polygons gives you an approximation of a near optimal space for a specific weather year. And as you can see, they vary quite a bit. They might remind you they might remind you of an onion, and they're kind of stacked on top of each other. And this represents that there's kind of more flexibility in different years. Some are more difficult and some are easier than others. So these are these blue shapes, and the yellow shape in the middle is the intersection, which is actually the area of investment that is feasible and near optimal for all the different years. So this is what gives you the robust solutions. And the cross in the center is just a solution which is very central to this intersection, because you can wiggle around a bit while still remaining in the intersection, which was kind of our main incentive. But these are just the total investments in those different technologies. So this would be aggregated over all of Europe in a one node per country model. But then we have looked at some different heuristics on how we can take these total investments and spread them onto the different nodes that we have in the model. And then, so we have solutions for kind of all of Europe that tend to be robust. And so what you can see here is we ran kind of our workflow that spits out a robust solution. But what we also did was we took all the weather data that we have and just ran a 41-year-long optimization. So this shows you the differences between the cost optimum over the 40 years and the kind of robust solution that's more resilient. And the different bars here, they show you the change from the optimal solution to the robust solution in investment. So you see a lot of shift. For instance, the really big bars that are pointing upwards are as in the UK, for instance, is additional investment into onshore wind in the robust solution. So you see some shifts, for instance, from the Iberian Peninsula there, but also offshore wind going from Sweden to Denmark. Yes, so this allows you to identify certain drivers or investments that contribute more to resilience against this weather variability. And just to wrap up with some final thoughts, so I said that we ran this for 41 weather years in one go as well. So why aren't we just doing that? So we did, but what we gather is that, first of all, running such a large model is computationally very expensive, and it takes a very heavy toll on the memory, which is not ideal. Not everybody has the resources to just use their university's cluster. So our workflow actually allows to just look at the single years and run them in parallel. So in fact, we kind of use a similar amount of resources, but this is all spread out on different computational nodes. So if you have a lot of time, you could run this on your computer. What we also want to avoid is that having such a model with 40 years allows you to really overfit the optimization to the data that you're observing. And you can, for instance, start saving up for 2010 and 27 already with storage. So this is what we're also trying to avoid with this approach. And finally, the idea is, of course, not to use past weather data to find the optimal energy system design for that, but we want to find something that allows us to be able to handle things that we haven't observed yet and something that's going to happen in the future. So for this, we're interested in finding things that allow to do this. Yeah, and then here are some references of the papers that I mentioned there with the numbers. And yeah, thanks for listening. Please ask questions, look at the preprint, look at the repository, or drop us a line.
Yeah, thank you very much, Aleksander. I think there's a really interesting question, maybe even to the larger community, from Zoltan in the chat that I would actually take for the Q&A after all the talks, but maybe one direct question for Aleksander from Patrick Kubicek, if you want to ask your question.
Hey, like my question was about methodology. How do you generate the scenarios for weather years? Like, do you just shuffle them, or?
No, so what we did is, you can get these reanalysis data for ERA 5. So we just took the different weather years from 1980 till 2020. And based on those, we generated artificial demand for all those different years. So you get demand, you get hydro, and you get renewable capacity factors from this. And then we really just take each year, year by year, in calendar year, but we've also tried some other things, if that answers your question.
Okay, so you take like actual estimates for each of the year, but the advantage of your project, you have many years and you can compare optimizations for different years. Okay.
Yes, so you can compare what comes out of each different weather year, one by one.
Thanks.
Okay, and one last quick question from Tom.
Thanks. I really enjoyed the paper. I had one question for the near optimality. You need to do this data, this aggregation of the capacities of each technology, and then you need to disaggregate it back into the model afterwards. And there's probably some heuristics there that you mentioned. Is the model actually then feasible over the 41 years, given this kind of complex procedure?
Right. So when we then disaggregated it with an optimization over the 40 years, then it was actually fully feasible.
You used an optimization for the disaggregation. Okay, that would be fine.
But we did different things. So we have some heuristics that don't use the full year, but just 1 year or 1 year, and then we just take the mean. And they're very close to being feasible. They're practically feasible, but not quite. There's a bit of load shedding that we need to allow.
Okay, thank you.
All right, thank you very much. Any additional questions we'll handle in the chat. And our next speaker is Tim Pedersen from Aarhus University. Tim is a PhD student in the Renewable Energy and Thermodynamics group, and his research is primarily within energy systems modeling and using modeling to generate alternatives as a method. And today, Tim will present a summary of his group's latest paper, long-term implications of reduced gas imports on the decarbonization of the European energy system. And we are very glad to have Tim with us today.
Thank you. So, yeah, thanks for the good presentation so far. I think we've touched on a lot of interesting topics. Right, so I hope you see my screen and everything as well. So in the spring, of course, the war in Ukraine sort of broke out, and we started this project looking into the long to medium term implications of reduced gas imports on the decarbonization of the European energy system. And the motivation, perhaps it's become clear to me that there's a technical motivation that I'll written down here in the slides, but there's a more there's a different motivation that lies behind, and I think that is that we wanted to generate some results that can have some policy impact, as Pawel and Thomas has been talking about here. Very often we do papers that are sort of have an academic interest and takes a long time, but sometimes it can be nice to do stuff that has more policy relevance and has a shorter turnaround. So that was really the goal of this project that we did, was to be sort of fast and use the models that we had at hand, and do something that answers some questions that are relevant right now, and then perhaps not have the highest sort of academic novelty. Yeah, but that was a bit of a side note. So the motivation, the technical motivation, can you say, the one that's in the paper, is that gas or natural gas has become an important part of our energy system as an intermediate or transitional fuel in the European energy supply. In 2019, it was 21% of our final energy consumption that was natural gas. And we see that a lot of the gas, or 70% of the gas used in Europe, is imported, and 40% of that has Russian origins. So our research question was how the discontinuation, the possible discontinuation of Russian gas imports will affect the transition of Europe's energy supply towards carbon neutrality, and what impact will that have on the technologies that will be relevant for the future. And a small disclaimer here. So we're looking at medium to long-term impacts. So we're not trying to answer questions of how we're getting through this winter or the next. We're trying to look at the bigger picture all the way towards 2050, and not so much here in the short future. So our assumptions, we went for generating a realistic worst-case scenario. So in our PyPSA model, we set in a gas constraint, limiting it to 3,100 terawatt hours. And just the quick napkin math that went behind is that in 2019, we had a gas consumption of 4,700 terawatt hours. 1,600 of that was had Russian origins, and subtracting those two numbers leaves 3,100 terawatt hours of natural gas left. And these assumptions mean that we don't expect any additional generation from European gas fields. It also means that we are not expecting a huge increase in additional LNG regasification capacity. We've also assumed that the energy demand stays unchanged compared to historic levels. And yeah, then sort of putting a little bit in the other direction, we've assumed that the cost of coal, lignite, and oil is remaining unchanged. Then we worked with two different CO2 budgets, one for a 1.5 degree scenario and one for a 2 degree scenario. Yeah, so just a small overview here. We're working with 4 scenarios, one for each temperature scenario, one where gas is unconstrained, we call this the baseline scenario, and one where gas is constrained, so the gas use has to stay under these 3,100 terawatt hours. The model we've used is the PyPSA-Earth. We basically copy-pasted the config file from Tom and Marta's paper called Speed of Technological Transformation Required in Europe to Achieve Different Climate Goals. So this was the model. We had it up and running. It was already on our cluster. We just needed to implement a constraint on the natural gas consumption, and then we could try and look at this new problem. The model includes 33 countries. It's fully sector coupled, so it includes electricity, heating, land transport, aviation, shipping, as well as industry and industry feedstocks. It has a 1 node per, not per country, per power trading region for the electricity transmission grid. And it has a copper plate transport model for natural gas. We then performed myopic optimization for 5-year time steps. Yeah, so straight into some of the results. Here we see the primary energy consumption for the baseline scenario, 1.5 degree. So of course we have time here on the primary axis and energy consumption on the secondary. We see historically the orange here is gas consumption. We have a quite high gas consumption, some coal, lignite, oil, the gray one here. Then a little bit of hydro, wind and solar, the blue and yellow, and then nuclear. And then we have ambient heat, this category, the green one, that's the heat recovered from heat pumps from the ambient air. And then, yeah, looking at how we transition here, we see that in this 1.5 degree scenario, natural gas is phased out rather quick. So already in 2030, we see that there's almost no need for natural gas, or at least quite small compared to historic levels. And we see how renewables become dominant already in 2030, 2035. So in the 2 degree scenario, we see how natural gas stays as a large part of the energy consumption all the way until 2040, 2045. And renewables only really kick in here 2045, 2050. So this figure here, we're still looking at primary energy, 1.5 degree scenario, but we're looking at the difference in energy consumption between the scenario where gas was available and the scenario where gas was limited. So the dashed line here is the limit we imposed on natural gas consumption, and everything above the dashed line here is the energy carriers replacing the missing natural gas. So in the 1.5 degree scenario, we see that natural gas consumption is replaced by some lignite use, some wind and solar, some additional biomass consumption, and some heat pump for heating. Looking at the 2 degree scenario, there's a bit more to look at. We see that we need to replace the missing natural gas for a longer period of time. We see coal with these black bars here playing a pretty major role in replacing the gas, at least for the the sort of near future, 2025, 2030. And we see wind and solar and biomass also taking up quite a big share in replacing the missing natural gas. And then we see heat pumps really playing a big role here, replacing natural gas burners in houses for heating with heat pumps instead. Yeah, there's a lot of results, and I can only show a few of them here. But here we're looking at some other metrics from the model. We can have time here on the primary axis, and then we have the annual total system costs on the y-axis up here. We have the 4 different scenarios. So the green lines are the 1.5 degree scenario, with the solid one being the baseline and the dashed being the gas limited. And what we see in terms of total system cost for the 1.5 degree scenario is that there's really no major difference between having gas available and limiting it, meaning that it isn't a big challenge to not rely on the gas imports in a 1.5 degree scenario, as it won't be much more expensive. In the 2 degree scenario, there's a moderate cost increase, indicating that if the ambition is just to have go for a 2 degree scenario, then it will actually have a high impact for several years, that we're not capable of importing natural gas from Russia. Sort of, the total system cost, we see that it's mainly driven by climate ambition. And we see here in the 1.5 degree scenario, it peaks in 2035, as we have that's sort of also where the implementation of renewable energy peaks. Yeah, and just a similar story here with the gas prices. We see that there's a big impact on the 2 degree scenario when gas is not, or when gas is limited. Quick touch here on LNG. We included a sensitivity scenario where we allowed the model to install additional LNG regasification terminals. And in this scenario, we see that it is using LNG in the first years here from 2025 all the way to 2035. But it becomes stranded assets for the remaining years. So the LNG regasification terminals would have to be built as new ones, and they have a lifetime of 30 years, meaning that the last half of their life, they will just be sitting unused. To quickly wrap up here, an ambitious climate goal will also alleviate the dependence on imported gas pretty quick. So there's a 2-for-1. You get a better sort of climate, and you also get rid of being dependent on importing gas from outside Europe. If we go for a 2 degree scenario, we'll have to delay phase out of coal and lignite. We'll have to deploy wind and solar capacities faster than what was already planned. And then we'll have to electrify the heating sector with heat pumps. Yeah. And then just to have a bit of an outlook here, we see that these findings that we've made, they are in line with the other studies by IEA and Bruegel. We've also seen that the dramatic ramp up required in installation of wind and solar in the 1.5 degree scenario casts doubt on the feasibility of staying below this carbon budget. Yeah, I think that was all that I could fit into these 10 minutes.
All right, thank you very much. I think we have one, I think it's a comment in the chat. And then if anybody else has a question or a comment, you can raise your hand. So it's Tom.
Yeah, it was just thanks, Tim. It's a very nice study. I was just thinking back to the question that Barry put to the first speaker. I mean, I wonder if you had the upstream emissions from LNG, especially the fracking fugitive emissions in the US, whether the 2-degree scenario might look a bit different.
Yeah, we haven't directly included those emissions in the scenario, but it's definitely been a thing. It was also discussed in the paper that there's actually some additional emissions upstream from natural gas that would also contribute to the emission levels of a 2-degree scenario here. And I think perhaps that is something we should work on including in our models, these upstream emissions from natural gas, as we've seen now that it's quite an important thing, and since more and more scenarios have been natural gas favoring natural gas lately, then perhaps it's even more important to include that.
I mean, it's a complicated thing because, I mean, if it's properly regulated, there shouldn't be any fugitive emissions, and it is possible. The Norwegians are much better at than the Americans and the Russians. So if everyone implements what the Norwegians do, then it would not be such an issue.
Yeah.
All right, we have 2 raised hands. I would, if they're quick, we can do both of them. So Tom, go ahead. Otherwise, we'll take one.
Okay.
For the breakout.
I'll try and keep it quick then. Maybe I missed it, but did you have industry representation, or when you talk about heat, are you explicitly just talking about household heating? Because you know, for example, in the steel sector and in other industrial sectors, there are discussions, or there were discussions before the crisis about gas as a bridge, and even with, you know, so DRI gas steel plants that then would go to hydrogen eventually. And I wonder if this demand for gas and these terminals are also somehow something to placate industry as much as, you know, the power sector might be actually relatively okay without gas now. Yeah.
Yeah, so in heating for industry is included. I don't know if heating for industrial processes, sort of high temperature heat, I think that is represented as a gas demand or oil demand rather than a heat demand. Tom, you can correct me here if I'm wrong, but I think that's how it's represented in the model. And we don't allow for fuel switching in the model, although I think that's been going on a lot.
I think Marcus Mullinger has done it, but yeah, this endogenous fuel switching is not in the base model at the moment, I don't think.
Who was that, Marcus?
Mullinger, I think I saw him. He's there. I think he did it at least for the heat, the process heat requirements. Yeah, I think he's in there. Maybe he wants to comment. I don't know if he's paying attention.
Yeah, sorry, I actually missed the question. Could you just shortly say it?
It was just I was just mentioning that but for the biomass study, you have endogenous process heat provision where you could switch the fuel.
Yeah, exactly. I can send you a link to my repository. So basically, we broke this and exogenous assumptions up a bit to include some competition. It does involve some problems with computational burdens, though. Depending on what you
I would love to see that. Okay. Definitely.
Yeah. Cool.
All right, and Barry, if you have a quick question, we're happy to take it. Otherwise, it's a longer topic. Yeah.
A very quick, short comment, just to say that I think there's some emerging movement now that this decomposition between a 1.5 degree view of the future and a 2 degree view of the future is not really great. That the Paris Agreement language should really be interpreted as a single integrated temperature goal. That what is typically taken as representing 2 degrees is like a 2/3 chance of meeting a 2 degrees limit, but the Paris language is well below 2 degrees, and you know, a 2/3 chance of limiting to 2 degrees is not really well below 2 degrees or meeting a below 2 degrees objective. And the carbon budgets for like 50% chance of 1.5 and say 75% chance of 1.7, and 1.7 is a reasonable interpretation of well below, are pretty similar. So it's not clear that they're, you know, that it's useful or helpful to think in terms of multiple temperature scenarios rather than just a single integrated well below 2 degrees scenario that is sort of 50% chance of 1.5 or 75% chance of 1.7. It's an evolving thing, but I think as the temperature impacts or the climate impacts become more obvious, then the idea that 2 degrees is something that it makes sense to be happy about or satisfied with, I think is really fading away. So that's just my comment.
Yeah, thanks. I think
thank you very much.
Yeah, in our studies, I think if we had more time, a scenario in the middle representing what you're talking about here, a well below 2 degree scenario would have also been nice to have.
All right. Thank you very much, Tim, and everyone for the discussion. We will move the break a bit. We're now going to do a quick bio break for everyone, give you a chance to get a new cup of coffee or tea, and we will start maybe actually a couple more minutes at, let's say, 11:03. So in 6 minutes, we'll start with Lin Yang's presentation on Energy Systems 2050. That's all right with everyone, and thank you very much. There's great discussion going on in the chat. Please keep that up, and I've already taken a couple of questions for the discussion later on that I will invite. And yeah, have a good break and see you in a couple minutes. Our second part of the session in the PyPSA user meeting. We will start the next 6 speakers with Lin Yang from TransnetBW, one of the 4 TSOs in Germany, and Lin will present their study on the Energy System 2050 that has recently been published. Lin, the floor is yours.
Yeah, thank you, Christoph, for the introduction. And I will share my screen now. Yeah, hello everyone. I'm very honored to be here to share our experience with PyPSA. This is my agenda today. I will shortly introduce our company, and this is also explain the reason why we are using PyPSA. And then I will introduce our energy system model, which is based on PyPSA-Earth. And we also did a lot of further development And at the end, I will share one of our important use case with our model. And this is Energy System 2050 study, which we just published several months ago. And we also present a result in Brussels and also in some other conference in Europe. And TransnetBW is one of 4 TSOs in Germany, and we operate the transmission grid in Baden-Württemberg in Germany. And we are also member of ENSOI, and we are designing the grid of future and transmitting energy across state and national borders. And we are working to make sure a stable and reliable energy supply. And here I would like to show some milestones of our energy system model with short name ESM, and this is based on open source model PyPSA-Earth. And from here we can see at the end of 2018, we in the proof of concept phase, we use PyPSA to do a pre-study in the strategical network planning. And there we decide to extend the basic model by adding features like we reviewed all the data sets, and we replaced a large part of data sets like power plant data and also power grid data. The main developments also include the consideration of the alternative technologies in the private road transport sector and also their optimization. We also add different kind of wind power and also conventional technologies. And from 2019 to until now, we are keep developing this model. And also at the same time, we did some studies. Like we in 2020, we published another study which called Electricity Grid 2050, which we gave an outlook on how electricity looked like in 2050. And several months ago, we published another study, Energy System 2050, which I will introduce later. And also at the end of last year, we integrate our ESM model in our own infrastructure, because now currently we are developing this model on AWS, in AWS cloud, and now we integrate in our own infrastructure. We use AWS cloud as development environment, and here are some more details of our energy system model. And currently, our ESM is a web application that can be operated completely in the browser. And we integrate PyPSA with Airflow. And because Airflow, there is a GUI, we can customize the GUI by our demands. And we can also combine SnakeMake workflow with Apache Airflow, and there we can add more workflow easily. And currently we can run up to 8 parallel simulations from different users. And we also add Zor and permission management to the system, and we customize the GUI. So yeah, for some colleagues, if they don't know Python, they can also easily to start the simulation just from the browser with some basic configuration of the scenarios. And now I will go to our last study, Energy System 2050, because Europe is aiming for a climate neutral energy system in 2050, with the study Energy System 2050, we want to provide perspectives for Europe's energy transition, and the main questions we aim to investigate are summarized in this graphic, like what role does sector coupling play in the future energy system, and how much infrastructure does energy transition need, and when do we have to start planning? Yeah, there are a lot of questions we would like to investigate. And and in this study, we have two central scenarios, and we assume that European Green Deal is established, which means that a reduction target of 55% by 2030 and climate neutrality by 2050. Here, to achieve the goal, we have two main scenarios, which are global markets. In this scenario, we assume that we can import hydrogen with a pipeline from outside Europe. And another scenario, energy resilient Europe. And in this scenario, there's no hydrogen import with a pipeline from outside Europe. And these two scenarios consider different possibility and possible development of hydrogen production and also availability. And here I would like to show a very small part of our results. We actually, the whole study is more than 200 pages. And here I will just show a small part. Here at the left side, it's the electricity demand in 2020 and 2050 in two scenarios. And we can see here, total electricity demand increases by 2 times from 2020 to 2050. This growth is mainly driven by Power-to-X. Electrolysis actually have the largest role. And then it's also in mobility, which also take a big share. And the overall increase is also because of power-to-heat, which is a electrification of heat sector by heat pumps. And at the right side, we showed a peak load from EU 27 countries in 2050 at the end of March. And from here, we can see that the peak load in EU 27 countries will increase more than 3 times from today. And flexible consumers account for 62 to 64% of total demand. And the largest flexibility comes from power to gas, and also in the central scenario, we assume that there's like 25% private electric car would like to contribute to the flexibility of power to the power system, which so smart charging and vehicle to grid. So, and here the smart charging of electric car account for like 60% of the total flexible electricity demand. And so, and yeah, thank you for listening. I just share a very small part due to the time limitation. And in our scenario, we take we take the simulation from 2020 to 2050 with 10 years steps with my OPIC. And yeah, that's my presentation.
Thank you very much, Lynn, for this well-prepared presentation and the well-designed study. There's definitely interest in the GUI discussion. Tom, if you maybe want to kick this off, and otherwise, if there's any other comments or questions, you can raise your hand.
Thanks, Lynn, for the presentation. It's great to see the TSOs using these open source tools and using the latest sort of methods. It's really fantastic. I was wondering about the GUI, because the GUI sounds quite sophisticated and quite in line with what some of the previous speakers had said they would like to see for PyPSA. Do you know if there are any internal discussions to share the code, or I mean, even if you can't share the code, just giving us some advice on how to, what technology stack to use and pitfalls would be already useful.
Yeah, we use Apache Airflow. It's cost loss, and it's also workflow. It's very similar like SnakeMake, but you can use the Python script in Airflow, or also use HTML script, JavaScript. You can freely use it there. And I can also share how our GUI look like. I didn't put it in the presentation because I'm not sure if I'm allowed.
No, it would be interesting for us to see it, actually.
Yeah, and wait a moment. I just take a screenshot, and here, sorry, it's too small, right? Okay, it's not. I hope you can see it. It's not very big. It's not big enough. And here it's our GUI. And from this page, we can start the simulation, because here I didn't make a screenshot for the whole page. And here this main configuration that we can tell the system where are our data, which where the data should, the output, where the output should be later returned, and which time resolution, and also clustering method. Because in our model, we separate generally into 5 or 8 parts. And so here we have the possibility to choose how many parts we want to separate, and also the supporting year, and also here the different constraints which you can choose. And we add a lot of more constraints to our model, so we have more flexibility. And then we can just one click, then the simulation will start, and later the result will be put in this folder, which we give here. Yeah, this is our GUI. And actually, because from what we can see here, we just have very basic configuration for our scenario, because there are a lot of input data. And we also think about how to make it more powerful, make this GUI more powerful. No.
All right, thank you very much. We have one more raised hand from Tom Kouroughli for a quick comment or question.
Yeah, I think, Lynn, it would be great actually, and if other people are interested in this GUI idea, please reach out to me. But at the very least, that we have a discussion on lessons learned when you were building this, and maybe even to. It sounds like you're not sure if you could share this publicly, but to have that discussion, I think would be very interesting.
That's for sure. Yeah.
Yeah.
On to our next talk, and let me quickly share the overview again. So we have Peter-Philipp Schierhorn and Andreas Hösl from Energynautics. Peter-Philipp is a senior electrical engineer at Energynautics and has 9 years of experience with global projects in power systems and renewable energy deployment. And Andreas Hösl holds a PhD from the High Voltage Lab at ETH Zurich, and he has, before joining Energynautics, he has worked as a data science engineer in industry. And so we're really excited for their presentation on spinning reserves implemented in PyPSA. And the floor is yours.
Thanks, awesome. Gonna go ahead and share the screen. So, yeah.
There, great, we can see it. So it's my turn to start, I guess. So hello, everyone. So Energynautics is a consulting company. So we work with grid operators, utilities, governments, and other power system actors worldwide, focused on the grid integration of renewable energy. And actually, Tom Brown used to work for us back in the day, and I was 9 years ago, I think I was kind of his apprentice when I started in the company. So here we are. This fits quite nicely to the last presentation from the transmission system operator, because we're using PyPSA for a number of different purposes in Energynautics, but in this bit here, we're actually focusing on the simulations of real-time operation and production simulation, dispatch simulation. So the actual hourly behavior of a power system based on the economics of the generators. And we're using PyPSA for a number of here in a couple of different countries and a couple of different projects. Right. So the background to this, just to go through this very quickly, I know there's a lot on this slide. The background is that in all power systems, we always need frequency control. So we need operating reserves or spinning reserves. I think everybody's heard the terms like primary control and secondary control that are needed to keep the frequency stable. Well, that has an impact on how our generators operate from hour to hour, because we need some generators to always run below full capacity to be able to provide upwards reserves in case a contingency happens in the grid or some other deviations happen. In these strategic studies in European or US systems that we've also seen quite a lot from in the last talks, this is often somewhat neglected, because with large power systems, the amount of reserves we need is relatively small compared to the overall power system size, and the reserves do have a relatively small impact on overall dispatch. That is a little different when you go to smaller systems, and we have a GIZ-funded project in Indonesia that we've been working on for years. And there we work with much smaller power systems, because Indonesia is obviously an island country comprising, I think, 600 power systems, 5 of them at gigawatt scale, and the other ones down to as small as 1 megawatts. And their reserves obviously have a much larger impact on overall dispatch. So, and especially if we start to integrate variable renewable energy, spinning reserves and frequency control are a constant headache in these smaller systems. And as we now have a project on the island of Sulawesi, which is a 2 gigawatt system, we're doing dispatch simulations in hourly resolution there using PyPSA, and we found the need to model operating reserves, so primary frequency control reserves, secondary frequency control reserves, and replacement reserves in a relatively detailed manner. That's the background to what we have done here. And with that, I turn it over to Mr. Hösl, who is actually our PyPSA mechanic who implemented all of this. And the floor is yours. Thank you very much.
Thanks. You cut me short if I run over the 10 minutes. I'll try to bring it across in 10 minutes. Right. So we come from the assumption when our generators providing reserves first depends on their capabilities. That is simple. That is basically just a factor that is given somewhere to be multiplied by their nominal power. Important part is basically that they need to have some headroom, obviously, so they cannot run at 100%, otherwise they cannot go up. And for some reserves, it's important to also consider downwards headroom, so I call this bottom room. And they need to be running, and we'll see an example of this. And this is about the difficulty of these different steps. The tricky one is that they need to be running. Okay, so then how many reserves do we need? This can either be, and in the following examples, I will use a very simple 50 megawatts. This can also be like the biggest contingency. This is relatively common. This can be, as a side remark, this can be set up linearly. So you can define your biggest contingency basically by bounding it from below. Or you can iterate over all generators, sum up the reserves and cover for each of them, basically. Or in Solarvisi, it's a bit more complicated. There's like a composite of 3 different requirements. Yeah, so we go with fixed amount. And then let's look at the, let's call it perhaps extra functionality, where we can put this in. How would we do that? So first of all, we define a new variable, reserves, that is defined for all generators and all times T. And then the first requirement is really simple. We just sum it up and require that they are larger than 50 for all for each time step, so for each T. We require that reserves are the individual reserves are smaller than the headroom for all generators and all T. And we require that reserves is smaller than the technical capability that generator can deliver. Note that this is just a number here. So this looks good, and this does nothing, as we will see in the following example. And the reason is, of course, that, yeah, see that in a second. So very simple example to add some plots here. Just 6 generators with increasing marginal cost. And they are supposed to supply this load. And obviously, they just get stacked on top of each other. Yeah, if we run this with the extra functionality that we just defined, we get exactly the same thing. And the reason is that just all the generators that are doing nothing provide nicely all the reserves, because they have all the headroom available, and we haven't yet required that they are supposed to be running. So for instance, if you take a look at this spot, this is a very tricky one that we would, for instance, have the worst possible scenario: 2 generators running at 100%, 4 generators completely switched off. Right, so how do we require them to be running? The first, obviously, is we use the status variable, the Boolean variable, and that immediately brings us into a mixed integer territory. We can obviously do that. If you remember, this was just a number, so we can easily multiply this by the status variable. And with that, we have functioning spinning reserves already. So we can take a look of how this looks like. This is going to be the result. Now the spinning reserves are, remember, they are only bounded from below. So before they went up to the maximum, because the solver had some leeway of where to exactly put the number. Now they actually cost money, and therefore they are limited down to 50. Right, this is what the generator supply. You can see here, for instance, that the cheapest generator now doesn't even run at 50 anymore, but it runs at some 45 and delivers a little bit of reserves here. Right, so mixed integer is the way to go for Indonesia, but for larger systems, we might need something cheaper. And we also have a cheaper version developed, which is, instead of adding a status variable, we bound the reserves. We introduce basically symmetric reserves. So we require an addition that reserves. I think I have the sign wrong way around. The reserves are smaller or equal than the power of the generator that is currently running, times of a constant that we can freely choose, and which pretty much sets the power at which the generator can provide its full reserves from below. And this is going to be the result. And the nice thing about this is this purely linear. This does not require a mixed integer, which makes it applicable to large-scale systems. At least we hope so. I think you can also see the resemblance between the two plots. So if you remember that point that I pointed out before, that was the tricky one where 2 generators are running. This is definitely now not the case anymore, but we have 4 generators that cover each other. And yeah, with that coming to an end, what else? In Indonesia, we needed something slightly more difficult. We needed switchable generators that can either provide primary or secondary, and this is subject to optimization. We also have some generators with efficiency curves that need to provide spinning reserves, and there's quite a headache at times. And then finally, the question came up: global versus local reserves. So all the reserves that we had here were obviously global reserves, and we only had requirements on those. But in that particular system, there's a couple of weak links, and we actually need reserves to be fulfilled in certain geographical parts. That just as a detail, and I think I kept my time, more or less.
Thank you very much. Perfect, perfect timing. There was a question in the chat about sharing the code, and Peter-Philipp already tag teamed that one and answered it. Tom, Peter-Philipp, if you want to expand on that, feel free to do so. Otherwise, if there's other questions, you can raise your hand and post them to Andreas and Peter-Philipp.
All the examples would be good. I think we already have a reserves example by Fabian Hoffmann in the PyPSA documentation. So anything that's novel. I mean, I'm not quite sure how discrete into what detail they have all the MLP constraints there in our version. Did you actually implement all these extra features that you had later? I'd be quite interested in the efficiency curve there. Is that already done?
Yeah. We had few options of what we were going to present here. We went with reserve because reserves, that's the one where I think it's not Witch's work, and we're definitely willing to also share that. Yes, we have the efficiency curves, and it's actually quite, as Andreas said, can be quite a headache. We do have nonlinear efficiency curves of stuff like gas turbines, co-generators, diesel generators. So that's okay. Of course, then that together with the reserves, that becomes quite an interesting piece of art, actually, because if you have generators with high fuel costs but a high partial load efficiency versus one with low fuel costs but a terrible partial load efficiency, you have a trade-off between the two, and sometimes also, I don't know, the optimizer tends to become relatively slow when you go too far with the reserves and the efficiencies. It's quite interesting, actually. Well, we can discuss about what we're willing to share and what we're not willing to share, but we definitely want to give something back to the PyPSA community, even though we're working with this in a commercial environment.
That's the spirit. Great. We have a raised hand from Koen.
Yeah, thanks for the great talk. Very interesting. So I assume that with these models, you don't do any kind of spatial aggregation, right? Or do you, and is it still relevant if you have any kind of spatial aggregation to think about these kind of more detailed reserve considerations?
Andreas, do you want to take this?
No, because I don't know. Peter,
yes, in this particular case, we're actually simulating this down to the last single individual generator, including a few digit megawatt size diesel generators. The reason why, that's what I said in the beginning, the reason why this is often neglected in this huge power system studies for Europe, for North America, and so on is obviously having enough reserve capability available still always matters, but it typically matters on a smaller geographical scale. If you start aggregating generators, you have to simplify this by quite a lot, and there will also probably be other imprecisions in your hour-to-hour dispatch if you go for a production simulation, and that's why it's typically neglected. So this is a special case where we're analyzing a relatively small power system with a high granularity, and there it really, like the way that reserves at dispatch really make a difference in terms of the overall dispatch, in terms of renewable energy share, and in terms of production cost of the entire thing.
All right, great. Thanks a lot.
Awesome. Thank you very much to our Energynautics presenters. We now have our 10th lightning talk from Anas Abu Zayed. Hannes is a senior researcher at the Hochschule Offenburg, focusing on modeling and optimization of energy systems and developing concepts to evaluate interactions of energy systems and power markets. And his talk today is going to be on MyPyPSA-Ger, a myopic optimization of the German electrical system. Welcome, Hannes. We're looking forward to your talk.
Thank you, Christoph. Just a moment. So you can see the screen, or?
So coming up. Yes. Thank you.
Perfect. So welcome, everyone. Today I will talk about our model that was developed over PyPSA Europe, MyPyPSA Germany, a multi-regional myopic roadmap of the German energy system. So to start with, we're from Offenburg, down in the southwest part of Germany, near Freiburg. A research team or a research center of 10 professors, 30 members. Some of them are also attending today, with most of our projects funded by either the EU or the state or industry funded. So since 2019, I've been working with Professor Niklas Hartmann in the Energiesystem und Energiewirtschaft research group. Along with my colleagues, we do intersectoral energy system analysis. We mainly focus on the industry and the transport concepts and future energy systems. So to give some parts of my presentation, first the introduction. I don't think I need a huge introduction for a variety of energy experts. So we try always to trigger the energy policy or the policymakers, how their decisions affect the energy system, the future energy systems. So it's a very dynamic, so this was the previous goals of Germany of 2050. It's a very dynamic, even more than the grid itself. With each new government, each new coalition, we have a new goal of the energy system. So the first, let's say the big question is, why a new model? There's already a variety of models. Why did we develop a new model? So the first thing is, of course, it's always difficult to keep up with energy policy or politicians. The second gap that we saw is that there is a myopic, let's say a gap in the myopic path of the energy system in Germany that will reveal more interesting aspects. So how will this energy path look like, and what is the optimal way to do it? Another topic or another point that we wanted to focus on is basically the regional versus national-wide renewable energy system potential. So with focusing more on regional aspects, to have a high spatial and high temporal resolution of a model. Of course, to do this, we have a very big server at Offenburg University that we are using. Otherwise, it would be a bit difficult to run the simulation. And finally, we have a detailed disaggregation of the consumption sectors, mostly the industrial sector, instead of having one node or let's say one load per node for the whole model. So how we developed the model, we started with the famous PyPSA-Earth model that is having some data only for the German energy system, that we have annual expansion planning or myopic planning until 2050 with hourly resolution and high spatial resolution as well, with detailed disaggregation of the consumption sector and the processes inside the industry. Of course, with some flexibility from the storage, electrical storage and hydrogen storage, as well as demand side management, mostly from the industrial, let's say, consumers. The new thing in this model is basically the regional potential and the maximum expansion rates, all of which to give us an idea how can we reach the optimal path towards the future energy system. So how did we exactly do it? We started with the basic model, a small snapshot or cutout from PyPSA-Earth for the German boundaries. We took the OPSD renewables, we mapped them inside the model, the OCGT and CCGT, the extendables as well, the initial capacities with some corrections, and mostly the generation profiles from Renewables Ninja, another great open source tool that we use. We remove any expired power plants, adapt the load and the CO2 limit. So all of which to start with 2020, our, let's say, reference year, with the actual status quo of the electrical system in Germany. And from there, we move on to up to 2050. So how does it exactly work? We start with 2020, having a yearly carrier limit per technology, a dynamic cost or load storage or line development. Each year we update whatever we installed the year previously. We update the CO2 limit or CO2 taxation or the allowance cost. We phase out if we want to in our scenario, we want to discuss a phased out technology or an expired power plant. The regional limits, I'll come to this in a moment. Then we have our mathematical optimization problem that we solve, and then of course we plot until 2050. So how does this exactly, the regional and the country limit work? So we have at each node, we have a technical potential and a theoretical, a theoretical potential and a regional potential that we introduce in the model. So the regional potential, the new thing, is basically the historical values that this region already seen, instead of having extremely higher values. So these are the new, let's say, constraints that we introduce to the model, and we run them year by year. So what can we done, or what can be done in our model? It's already on my GitHub published, I think, since the beginning of this year. So we have dynamic cost assumptions that we can have per technology, or either in terms of capital, marginal cost, and so on. We have regional and national investment limits per technology as well. A CO2 budget estimation for the whole energy system or the whole energy transition path. Of course, we can translate the policy reforms in terms of, or into equations to have more kind of, what does this policy decision or so on, what does it imply on the energy system, estimation of the energy transition cost and optimal path, and much more. I'll just show some reference cases that we already did. I think Tom mentioned in the beginning that it's already 7 years since PyPSA was published. So, and this is the first user meeting or workshop, so a lot to catch on. So our latest study was an embargo on the Russian fuel. So we did this in March earlier this year, that we say, okay, how will this, what is the implication, or what does it mean in terms of equations on the energy system? And again, some cost assumptions. Will it be a price shock that the market basically will explode, what it already happened, or will it only be a wave? Another study that we did is basically the Easter package, which was also published later on in June, with the Minister Robert Habeck saying by 2035 we will have a fully decarbonized or fully 100% renewable electrical system. So we tried to simulate this myopically with the numbers that the minister proposed, and see what are the differences, where did we go wrong, or what did we focus on. Mostly it's the hydrogen economy that made the whole difference. Another one is the 2050 carbon neutral energy system. So this is also again done in the model. It can be, I would say it needs a bit of Python expertise to use it, not as already Max already proposed in the first presentation. So it is a bit of a drawback. Not everyone can use it, but it's not that complicated to be used. Again, we have yearly results of the generation or of the installations, which regions were focused on which technology and so on, what kind of infrastructure do we need and where do we need it. Another scenario that we also studied is the strong sector coupling, basically having a 1,400 terawatt hour demand by 2050, which was also proposed by Fraunhofer ISA. And we found out in the study that without huge investments in storage or interconnections, this cannot be done. So another output of the model, or which is why we basically developed it from the beginning, is the regional aspects. So which region is focusing on which technology year by year, what is the implications of the regionality differences in Germany, how can it be triggered completely or correctly. And finally, or let's say one of the other things is basically the energy transition cost. So what exactly did we pay at this year for what, and so on. The CO2 budget, as I mentioned before, we can have different scenarios being studied or being simulated. What kind of emissions or what kind of budget do we have for this scenario, and so on. So for future work, just to finish with, first we have the European interconnections that we're currently trying to do without, or let's say implement without having the same model as PyPSA-Earth. So PyPSA-Earth already did this. We don't want to copy paste it, but having a node per interconnection to have Germany as an energy hub, but with more regional or more detailed disaggregation inside Germany, and only one node per interconnection. The other thing is basically what I'm currently doing, I'm kicking off my PhD, is a demand responsive industrial, or let's say consumption sector. So we have, it's again another open source tool, a very powerful tool, Demand Regio, from FFE in München, that they have a very detailed and disaggregated energy consumption for the CTS, the industry and households. So what I'm trying to do is basically have synthetic load profiles that were developed per industry type by my colleagues, Hani Kim and Anna Zendas, and implement them inside the model. So instead of having one load per node, we can have different loads, different flexibility potentials from each, let's say, industry process. It's a small, let's say, storage. So this is only an exemplary or illustration of how we are doing it. Is basically by using a store element from PyPSA to use it to have extra demand at other times and extra generation, or basically flexibility at times of need. I hope I'm still with time. So thank you again for the opportunity, Christoph and Tom. It's great to have this community to speak with lots of interesting projects, and hopefully we can do more of this again. Thank you.
Great. Thank you very much for this presentation. There's a quick clarification from Tom, which I'm just going to pose to you. The CCGT and OCGT in 2050, is that hydrogen or carbon capture? No, or
that's normal natural liquefied gas, so it's not hydrogen.
Hydrogen. And you compensate.
It's unabated?
Again, sorry?
It is unabated?
I cannot follow it. What is it?
Do you have low emissions for that, or do you compensate with some carbon capture or offsets? Or
basically, one of my colleagues, I'm not sure if she's also here attending today, Marichel, she's doing the carbon capture by using biochar. So that's how we compensate for the emissions.
Okay, but I'm sorry, just quickly, since I'm here. In 2050, you don't have zero or negative emissions in the net.
In this study that we did, no, it was 95% reduction, not 100%. Yeah.
Okay, thanks.
Nice. Then we have a question from Mirko Schäfer in the chat, and then a raised hand from Mohammed. Mirko, are you here?
Yeah, but I think my question was already answered. So I was curious about the consumption disaggregation, but you use the demand regio, the disaggregator. Okay. Did you put any validation on that additionally, or you just took over their disaggregation routines?
I think most of the validation is from the official published values from either the grid operators or the NCOE platforms. That was most of the validation that we did. It's difficult to validate when you have different, let's say, references or numbers.
Okay, thanks.
Mohammed?
Yeah, hello.
Hello.
Thank you, Anas. It was very interesting. I have just a
a question and also observation. To start by the observation, I think that your work, it's very interesting. I'm working on the same area, which share a lot of similarity in our work. And I think that the OCGT and CCGT have also the ability to be a part of energy system as a system which allow decarbonization, because the same installation need only some modification to be able to burn hydrogen and produce green energy. So it's my observation. It could be a great interest to make big contribution in the reduction of dioxide emission, and also to meet the Paris Agreement to -2 degree by 2050. For my question, did you put in action any program or model to remove dioxide of carbon, and did you take into account by 2050 or in a scenario to reduce dioxide carbon emission? Thank you.
Yeah. So to answer this question, this is basically the work of my colleague, this carbon capture or carbon storage. I didn't really do it. It was Marichel. I'm not sure if she's attending today or not, but she's the one who basically did this as part of her work. So, and for the hydrogen being run in the OCGT and CCGT, I think we wanted to do it, but I think we reached the conclusion that you cannot do everything in one model. So this was the first. Just a disclaimer, because I just saw it from Robbie. The new goal is 2045. We also did, after we published the first one, that we did another study. I can send you the links afterwards to see the differences within 2050 to 2045. But it's as I said in the beginning, it's very dynamic. It's roughly difficult to trigger it always and be on time with new policymakers and so on.
Thank you. Just another observation. I do that. I can share with you also some model and some technology to do that, and you can integrate it easily in your work. And so we can speak about that later.
That would be great. Thank you very much.
Thank you.
All right, great, thanks. I think there's another 1 or 2 questions in the chat from Fabian Hofmann, for example. Maybe you can answer those there. And we will move on to our next speaker, Paul Regentin from University of Freiburg. Paul is a master's student in Freiburg, and he is writing or wrote his thesis on low demand scenarios for European energy infrastructure with the Department of Sustainable Systems at the Freiburg University. We welcome Paul, and looking forward to your talk.
Thanks, Christoph. Let me just share my screen really quickly. Okay, so thanks for the introduction. I'll be talking about low energy demand scenarios for a robust energy transition. And this is still being written, unfortunately, as a master's thesis. But so basically what we want to do here is fill in a research gap in the area of low energy demand scenarios. There's been a lot of research published in the last couple of years, especially in the last couple of months even. But basically the sort of groups of models that are out there are either IAM, integrated assessment study models, which aren't so good at representing local flows of energy and can't really, because of the way they balance with heuristics, you can't really see how system dynamics might change because they're more fixed. There's also quite a few national studies for France, the UK, Ireland, and Germany, for example. These, though, can't really represent cross-border flows in a very high-resolution way. And for example, I think in 2019, 19 European nations had more than 10% of their electricity imported or exported. So it's an important aspect of the system. Furthermore, as renewable penetration increases, we'll likely see a higher concentration of energy generation and production that is sort of necessarily excluded from a single country model. And then the final thing is they typically use a model that's built for the specific country, and those aren't generalizable or comparable. So what we're doing is using the PyPSA-Ger SEC model to explore low energy demand scenarios for all of Europe, using a bottom-up energy system model with full sector coupling. Furthermore, what we want to do is not just look at what happens with low energy demand scenario, not just take like the single optimized model result, but explore how the low energy demand can make the European energy transition more robust. And by robustness, we're taking the definition of models and solutions that are acceptable under a wide set of plausible conditions and configurations. So the basic scope of this project is that we take in the existing PyPSA-Ger SEC model and then modified it slightly to allow for the tuning of demand levels. Then we really just borrowed low demand scenarios from an existing study, plugged them in, and ran the model to get the optimal generation and operation of the system. And then after that, we looked at a couple non-optimal scenarios, is what we're calling them, where first we look at what happens if the changes in demand aren't as large as they're projected to be. Then we look at what happens if emissions targets are missed or abandoned and how low energy demand affects the system in that case. And finally, we look at what happens if the sort of ground parameters of the model are pessimistic, if they make it harder to achieve net zero. So yeah, this is just what I just went over. We're going to start with the 2050 net zero scenarios. So we took these demand levels from the EU calculator. There's a web tool online, and the whole project is open source, so you can get quite detailed demand information at the sub-sectoral level, and they match quite well with how PyPSA models demand, because it's taken from the same sources. So from this, we took a baseline scenario which follows basically the EU long-term strategy. Then 3 low demand scenarios, one which is based on efficiency policies, one which is based on sufficiency policies, and then the tango scenario is, I guess it comes from the phrase, it takes 2 to tango, so both efficiency and sufficiency based reductions. So this is just basically the initial results in terms of total costs. The first thing I want to point out is that the maximum demand reduction was almost exactly 50% from the EU Calc study. What we see, though, is in the major metrics that we're interested in, so costs, the use of direct air capture, and then the amount of renewable generation that needs to be installed, we see over 60% reduction. So the conclusion that we want to draw from that is that the benefits of lowering energy demand are sort of disproportionate. You get back more than you put in when you reduce energy demand in the system. And then also we can see where these savings occur. So you can see, for example, carbon capture and storage costs almost disappear. Fuel costs for oil and gas also drop significantly. And then the costs for installing new power generation also drop. If we look at how the carbon balance, you can see here again, direct air capture disappears from the system in the lowest demand scenario. We can also see there's a bit of a rebound in gas consumption. That's because there's more space, because the emissions from transportation, industry, and aviation are drastically reduced. The next sort of part of this study is to look at lower levels of change in demand. So a 50% reduction in final energy consumption would be a very massive project. So we want to look at what happens if we can only get 40% or 30 or 20 or 10, for example. So this will tell us where the benefits that we've seen occur, if they occur sort of linearly throughout, or if there's tipping points or something like that. What we see is in terms of cost, the costs decline more or less linearly. You get a slightly larger benefit at the first reductions in demand. So about 84 million euros in annualized system cost per terawatt using present day levels of demand. But if you drop down to the near 50% value, it's only 62 million. Where we see a sort of nonlinear dynamic is in the carbon price. So we see these different regions. This flattening out here is where biogas is removed from the system. So that constant cost is basically the cost savings in, by switching from biogas to gas for a ton of carbon. The heating technologies also show nonlinear dynamics. You see, again, a bit of a rebound in gas boiler installation, and that's because there's less emissions elsewhere in the system. And so the cheapest sort of peak load heating technology is a gas boiler. However, what we see is there's not a total increase in conventional heat sources. They sort of take up around 200 to 250 terawatt hours per year for all scenarios, but then heat pumps just don't need to be used as much. Our next scenario is one in which we assume that renewables aren't built fast enough. What we're seeing from industry reports compared to the government targets is that it's quite possible that we miss targets by up to 30, maybe 40% in the next 5 to 10 years for solar and wind. And so we want to explore some scenarios in which that happens and possibly the political will for the energy transition isn't there, and how low energy demand affects the system in those cases. So just a quick explanation of what's going on here. We have 3 scenarios in which 60% of the necessary renewable capacity is built, one in which 80% of the necessary capacity is built, and then one in which 100% of the necessary capacity is built. But for this, we run it without any emissions limit or emissions target at all. We see the same generally linear decrease in system costs, but the most interesting metric here is the difference in costs between the net zero scenarios, which are represented by these dashed lines, and the no emissions limit scenario represented by the solid lines. And that difference is represented here. And you can see by reducing energy demand, the difference in costs between no emissions limit and net zero declines quite rapidly. If you get down to about 8,000 terawatt hours per year of final energy consumption, you're around 5% or lower difference in costs. So it makes a net zero system much more comparatively affordable. Also, in terms of emissions savings, we see 88 to 90% emission savings, even without fixing a carbon limit due to energy demand reductions. The fourth study that I'll go quickly through, because I think I'm running low on time, is what happens if the global parameters that we're assuming aren't correct? How much savings would lower energy demand provide in these cases? So basically, we took a set of 7 global parameters: the amount of internal combustion engine transportation used, the gas price, costs of direct air capture and point source carbon capture, and then the potential of renewable energy per geographic area and the potential of bioenergy per geographic area, and then the presence of a hydrogen network. That's 7 scenarios. So each one with a low and a high value, giving us 128 scenarios, which this plot shows the increase in costs as relative to the base system costs. What we see is that with low energy demand, the median cost increase is lower, with a 50% median increase for the low energy demand scenario versus a 20% median increase for the baseline scenario. The biggest benefits, though, occur in the upper quartile, where the possible cost explosions are significantly higher for the baseline scenarios. The one last thing that we see here is there's some groupings of scenarios, and what PyPSA allows us to do is see what groups of parameters define either a very low price increase or a very high one, or one in which the baseline costs are much higher than the low energy demand costs. What we see is to ensure low energy demand or low price increases, sorry, we need to have no internal combustion engines used for transportation and low carbon capture costs and low gas prices. The worst possible scenario where we see large system cost increases is if we can't remove internal combustion engines and then carbon capture costs are quite high. And then finally, the place that sort of low energy demand helps the most is if we have ICE cars on the road and the costs of direct air capture remain high, but then point source carbon capture is not increased. So that's basically my presentation. We sort of conclude for now that demand reduction is a cost-effective strategy that can reduce needed renewable capacities and as well as negative emissions technologies capacities. Yeah, so let me know if you have any questions. Thanks for your attention.
Great, thank you, Paul. We have time for one or two questions or comments. And Tom Kouroughli, you have a raised hand.
Yeah, thanks, Paul. This is really super interesting study that you're doing. I just wondered if you have some kind of hierarchy of low, well, like the high efficiency, what's the word? Implementations, like the policies or the technologies that you're implementing that have the highest bang for buck, basically. So like going down, starting with what's the most effective, cost-effective efficiency measure, and then going down from there. I think that would be super interesting to see.
Yeah, I agree. The problem is that this is a master's thesis with like a tight time deadline, so we haven't been able to go into that. The EU calculator uses, I think, 71 different policy levers as well, so it would be like pretty time consuming to go through all of them individually. But yeah, I think that would be a valuable way to take this further. Yeah.
Great. Awesome. Thank you very much. I believe we are moving to our next speaker. And second to last, we have Carlos Epia from Hochschule Flensburg. Carlos is a electrical engineer with a master's in energy and environmental management. And he currently works as a scientific researcher at Hochschule Flensburg. And he will present on the EGON project, Open and Cross-Sectoral Planning of Transmission and Distribution Grids. Carlos, the floor is yours.
Thank you. Okay, so once again, hello to everyone. My name is Carlos Epia, and I'm going to talk to you very briefly about the EGON project. So first of all, the EGON project is financed by the Ministerium of Economic Affairs and Climate Action, and it has 6 members, 3 universities and 3 research institutes, the ones that you can see on your screens. Okay, officially, the EGON is an open source planning software designed to calculate the optimal network expansion and flexibility options for Germany, giving an electric network integrated to the gas, heat, and e-mobility sectors. It started in 2019 and will finish in 2023, March. That's why the results that I'm going to show you at the end are not the final ones, but preliminary ones, or an example of how our final results would look like. So EGO is a software that integrates several tools, and these tools are divided into 2 groups. The first group is to create a data model, and the second group is the electricity grid planning software. So briefly, to give you an overview, we have the EGON data tool, which is the data model creator, Dingo, which creates synthetic distribution grids. Also, we have, on the other hand, iTrago, which optimizes transmission grids, and iDisco, which optimizes distribution grids. In the center of everything, we have a database that will be available online at the very end of the project, and we will be happy to share with you. Okay, how do we approach this problem? We choose a top-down approach, where we started with the extra high voltage and high voltage networks from Germany. So we use PyPSA to optimize the dispatch, the network expansion, and different parameters more in the very high voltage level in Germany. Then, based on those results, we optimize the middle voltage networks. And finally, we disaggregate these middle voltage results into low voltage networks, where at the end we will have a built-in resolution results. Now, to do that, we created two different scenarios. The first one is called EGON 2035, and it is based on the NEP 2021. And the second scenario is the EGON 100 renewable scenario, which is, of course, based on 100 renewable sources. It is based and created based on PyPSA-Earth and using our own calculations. Here you can see the model concept for the EGON 100 renewable scenario, where you can see different sectors like electricity, gas, heat, and e-mobility. And something important that I would like to share with you right now is that the green elements are predefined in the scenario. For example, the power plants are already allocated, and the capacity of the power plants, electrical power plants, are defined in the scenario itself. Meanwhile, elements like batteries, salt-covering storages, or fuel cells are going to be optimized, allocated, and sized based on the optimization process. And now, let's start with EGON data. So EGON data, as I already mentioned, is the data model creator. It helped us to create the two scenarios. So just to give you an impression, on the right part of the screen, you can see the electricity and gas grids that we have, the buses and the links. As you can see, we also included the foreign countries, the countries that we selected, which consider that are more important to get acceptable results at the very end, since we didn't want to work with an isolated system just for Germany. Just to give you some numbers, we have more than 31,000 buses, more than 10,000 transmission lines, and almost 50,000 links, where links are the connection between different sectors or inside the same sectors when they are not the electric one. Okay, once the scenarios were created, we use our first tool, is iTrago, which optimizes transmission grid. It is public available, and you can find it in GitHub whenever you want to take a look. Okay, so iTrago performs some steps, and as I already mentioned, we have scenarios with very high complexity and which are very accurate, but they are not suitable to run simulations with acceptable running times. So the first step that iTrago does is to perform a complexity reduction. We have complexity reduction methods for space and also for time. So, for example, in terms of special complexity reduction methods, we have k-means and k-means Dijkstra, which is the one that we are going to use in our final for our final results. And talking about temporal complexity reduction, we have segmentation, snapshot clustering, and skip snapshots. Now, what we want to get at the end of the calculation based on eTrago. We want to be able to allocate the network expansion requirement per scenario and per line, and how much it's going to be necessary, as well as the storage, as you can see in this map. But more than that, we want to be able to dimension and locate fuel cells and electrolyzers for the hydrogen case. We want to see the generation dispatch and other results that will be more clear in the coming slides. So based on the results of eTrago, we go to our next tool, which is called eDisco, which is in charge of the distribution, the optimization of distribution grids, which includes middle voltage and low voltage, also available in our GitHub repository. So what can eDisco do? It's able to perform conventional grid expansion, curtailment, and storage integration based on the eTrago optimization results, and finally perform a load flow analysis based on the PyPSA library. At the very end, we have the Ego software, which is the one who integrates everything, and also it's available in our GitHub repository. And at the very end, the results will look like this. So we have every single unit here is a medium voltage grid district, and it's just a preliminary result, like a test that we perform. We are going to see the optimized network expansion. We are going to be able to see how much does it cost to expand the grid, how much does it cost to expand the storage. Also that for every low voltage level, and it will be available for the full country, but in the future, because in the coming months, in March, I would like to do a little bit of advertisement here. We will have our final workshop in Berlin, where we would be happy to share the final results of our project. And yeah, in case you have questions or comments, you can contact me, or you can go directly to the EgoN project webpage that you can find here. Thank you so much for the attention.
Are there any questions or comments? Mirko Schäfer.
Yeah, thanks. Yeah, thanks for the presentation. Looks really great. I was just wondering, you represent Germany in this super high resolution with all these lines, and then the surrounding Europe, very, very costly. So isn't that a problem for your model? So why didn't you use a little bit more resolution around Germany in this picture? Exactly stands out.
Because we want to of course be able to show the interaction with the foreign countries, but our main objective is not the connection or the network with the corresponding neighbors. Our main objective is inside Germany, so we want to optimize the flexibility options and the network expansion, but inside the country. That's why the foreign countries are represented just by one bus.
All right, thanks. Another Koen, yes.
Right, super quick question. Hopefully this is not a silly question, but does the EGON project also have anything to do with the ERMOF solver, or is there no link there? I thought that I saw something about this at some point.
No, not really. We use eTrago, at least, is based. The structure of eTrago is based on PyPSA. We don't use ERMOF for any purposes in this project.
Okay, yeah, sorry, I probably mixed something up.
No worries.
All right. Any other questions or comments? If not, we are staying with Koen and moving to our last talk. Koen van Greevenbroek presenting PyPSA Longyearbyen, a simple model with electricity and heating sectors. And Koen is a PhD candidate in energy systems modeling at the Arctic University of Norway. And he has a background in mathematics and is excited about open data and research, and will share his talk with us today. The floor is yours.
Right, thanks so much. And you should now see what's going on here. Yeah, so I have to say I'm just really impressed by all the talks so far. I've really enjoyed all of them. We're going to switch gears a little bit now. You know, we've all been concentrating very hard for a long time, and this last talk is going to be a little bit more relaxed. I'm not presenting any kind of huge project or big results, but we're taking a slightly different perspective now on what it means to use PyPSA. I'm going to talk about a model that I developed quite quickly for Longyearbyen, which I'm going to introduce very soon. And we're not even going to look so much at the results, but a little bit at the implementation. And then I'm going to talk a little bit about how I think that this could be potentially useful as a learning resource. It kind of fills a gap there. Yeah, so maybe not everyone has heard about Longyearbyen, but it's the biggest town on Svalbard, which is like all the way in the north in the Arctic Sea. It's one of the northernmost permanent settlements. There's some research going on there, some tourism and coal mining. And up until now, the town has been run on coal power. There's one coal power plant, but a transition to renewables is being considered. I mean, it's kind of yeah, bad that there's this coal power plant running literally in the Arctic. People want to get rid of this. And so I was in Longyearbyen a little bit more than a year ago for a PhD course, which was about exploring this energy transition, what the opportunities for renewables were up there. And that was the basis on which I developed this model that I'm going to talk about. And so, okay, where could we start? I mean, we got some data for what the energy situation actually looks like up there. You know, you have some electricity demand, you have some heat demand, and especially the heat demand varies quite a bit over the course of a year, of course. They have a district heating system there, which runs directly off the coal power plant. And then we got some wind power capacity factors. That was actually like Alex, who's also here, Aleksander Grochowicz, worked a bit on the wind capacity factors. We got some solar capacity factors, which, as you can see, are just completely zero from mid-October till March or so. That's because of the Arctic night. The sun is below the horizon. And the main objective here was to look at the potential for energy storage here in combination with renewables. So I developed a very, very simple model based on PyPSA, and you can kind of see the energy flow here. So we have some electricity demand, some heat demand, and we can couple all of those things together with various connections. So I'm not going to talk about too much detail, but we included a number of different storage technologies here, like battery storage, hydrogen storage, hot water storage, and then some other fancier heat storage technologies. And all of this was made expandable in the model. And then we had about 8 years of at least of capacity factor data and just 1 year of demand data, which we kind of like concatenated into 8 years. And just with this very simple setup, we actually already got some quite interesting results. So apparently you don't have to, like you don't need a huge complicated model to already get rather interesting behavior. You really see how different kinds of storage technologies can operate at different timescales in this model. That's kind of where we like what we were after in this project. The interesting thing is that this was done in just about 400 lines of code, and the whole thing was developed in about 2 weeks or so. And we tried to also put some focus on making the model easy to understand, the code easy to read. We documented it reasonably well, so you can find it at the GitLab repository here, and it kind of includes everything that you need to get started with this. It has rather minimal dependencies. All the data is there. There's also some analysis notebooks included. So I actually think that this is a nice kind of it sits in a nice sweet spot between some very simple examples of how to use PyPSA and the more like bigger, complicated projects. So yeah, I should also say we don't use SnakeMake here, but it's just a very simple setup where you still just read some configuration and cost data from external files. Yeah, and so issues and merge requests are welcome. And I think that if you want to get new people involved with PyPSA, or if you want to find some kind of learning resource, this might actually be useful as a kind of example of a very self-contained, simple project that has everything included, but still is actually interesting, gives some good results, and is easy to play around with. Yeah, actually, that was everything. So short and sweet, different perspective. I'm happy to take any kind of questions. Thanks for your attention.
Thank you, Koen, for your presentation. Are there any comments or questions? Robbie, please.
Yeah, can I come back to my original question? What requirements to entry would you say would be useful for a user? Obviously, some knowledge of Python, some knowledge of the command line.
Yeah, that's a very good question. So I think some knowledge of Python is required, and then we use some Jupyter, we have included some Jupyter notebooks for the analysis, so you need to know how to run those. But in general, the technical requirements are fairly low. So I think if you know your way a little bit around Python, then you should be able to get into this model without knowing too much specific details about the energy systems modeling, PyPSA in particular, SnakeMake, this kind of stuff. It's not, you do need to know how to program a little bit, unfortunately still. So I don't have a graphical user interface for this.
Thanks. There's a question from Leon also, Leon Schum in the chat. Sorry, can you speak? Yes.
Great presentation. Especially love the vertical code you put in your last slide. It looked really, really nice. I had a short question about the demand. So middle of July, there was a huge demand drop in electricity and heat, I think. What's the reason for that?
Yeah, wait, maybe I can again share my screen here so we can get back to this. So you probably mean, if I can get this, no? You mean this huge drop, right? So I agree, this looks very suspicious. We heard rumors from the supplier of this data that it's probably related to the coal mine, which itself is a pretty big user of electricity. And they might have like had some maintenance at that time or vacation, or so at least that explains the electricity demand. Why the heat demand also dropped is mysterious, so it might honestly just be bad data. And in that sense, like I'm not giving any guarantees that this is perfect data. And also I have to say the cost assumptions and the technology assumptions could probably do with more scrutiny before this is given directly to the policymakers. Yeah, but thanks for the question.
All right, thank you very much. I believe this about concludes our lightning talk.
We actually promised that the Fabians would show a brief few slides on the current development plans for PyPSA and PyPSA Europe. I know everyone really wants their lunch, and it's been a very long day. But maybe we should just take 2 minutes for that, Fabians. Do you think you could compress it a bit? We've talked a bit about the GUI development, and we need to obviously do on the learning materials a bit more. But do you want to just flash the slides on the developments of the core models, and then we can let everyone go? Well, obviously you can go anyway. But
of course. I think we can do it. Fabian, other Fabian, so squared Fabian power. Fabian, do you want to start?
Yeah, I start. We keep it very brief. So yeah, we just want to give you a short outline on what is happening within the upcoming versions of PyPSA, PyPSA-EUR and PyPSA-EUR-Sec, and where we focus during the next development steps. So for PyPSA, if you are on the mailing list, you probably saw that already, that we are working on a new optimization module, which is based on LinearPy. Why are we doing this? We saw that many users have problems with the native code that we implemented for PyPSA for improving the performance. And this is why we made the decision on moving all this optimization code into a standalone model or a standalone Python package, which is called LinearPy. And that was done recently. And now this LinearPy optimization module is integrated into PyPSA. You probably, so the main function here is the nOptimize function, which will replace in the long term the nLOPF function. And when you switch to that new optimize function, you probably see some different behavior, but we have a migration guide, which is online, and there will be some introductions. And whenever you see any problems with it, please shout out and we will be happy to support you. The second point is there is a new piecewise linear approximation for transmission losses. So there is a linearized way to optimize the LOPF or to optimize your network with transmission losses. The third point is that we want to include technological learning in the pathway optimization in PyPSA. So that is a nonlinear optimization where you would see how prices are decreasing depending on the investment into a specific technology. So Lisa Tyen, one of our colleagues, was working on this, and this will be integrated into PyPSA. The fourth point is that we want to make usability of the PyPSA tool improved, and this tackles that we want to provide front-end statistics and better visual module to our users. And one part of this is the nStatistics function. This is for technical detail. This is a function which also has tailored functions in the background. And you can use those just to have a really front-end information on how your network is behaving, what are the energy outputs, what capacity was installed, and what are the prices, and so on. So really to get a first glimpse of your network and what does the optimization give you. The fifth point is an improved consistency check. So, and feasibility pre-checks. We saw that many users have problems with infeasible models, and they just standing there and they asking themselves, why the heck is it not feasible? And we want to improve this. So this is why we want to improve the consistency checks. And also, whenever you have a problem that is not feasible, where there is a formulation in the background that can give you hint which constraint can be non-feasible. And this is then also related to the linear pi optimization module. So there will be some calculations, which is at the moment only given by Kouroughli, that can give you the infeasibilities of the network. The second last point is the generalized time series aggregation, which is based on TSUM. So we tackled this in one of the talks. I can't remember right now which one it was. There is segmentation of time series that you can aggregate your time series and make a smaller set of representative time steps within your model. And the last step is that we want to expand the collection of ready-to-use models. So we see there's so many models and so many working groups and research centers working with PyPSA, and we want to have a collection where you just press or you just write out one command line and you get that network that previously was uploaded somewhere. And it would be, I think we have to figure out where this platform will be. I think it will be on Zenodo. So there will be a getter that retrieves data from Zenodo and then downloads it in the background onto your laptop. And then you can use this model. And so that was it for PyPSA. I hope I kept it brief. And now Fabian Neumann will go on with PyPSA-EUR and PyPSA-ERSEC.
Yes, I'll just flash a few bullet points. We're planning for our European modeling in the electricity system only model and the sector coupled model. So for PyPSA-EUR, we've been working at better representations of offshore energy and solar energy. So you can expect some news on floating wind turbines and more detailed analysis of hub and spoke connections offshore in the North Sea or the Baltic Sea. For solar energy, we're going to add new technologies like concentrating solar power and axis tracking PV. We've heard presentations this morning from Alex and Koen that have analysis, and Georg as well, that have done analysis for multiple weather years, and we will make it easier to sweep through different weather years in PyPSA-EUR by adding a wildcard for the weather year. So you can actually use all the weather data available in ERA 5 and and do a more comprehensive analysis of the weather variability. We've been repeatedly asked also to provide alternative ways to cluster the network. So right now it's based on the grid topology, but many people also would like an aggregation based on administrative regions like the NUTS or GADM definitions. For PyPSA-ERSEC, so the sector coupled model, so far we have implemented pathway optimization with myopic foresight, and Lisa Zayin has published a preprint on integrating technological learning and pathway optimization. And we want to include that in the main model branch, that we have pathway optimization with perfect foresight so that the model can endogenously decide when it wants to spend its carbon budget and how quickly it transitions. So with the sector coupled model, our model, and particularly with the industry inclusion, our model develops a little bit more into the direction of a material, or sort of moves into the direction of a material model as well as combined material and energy models. So we have to put some work into that direction as well, where we add rather material demands than energy demands, and then endogenously optimize which processes and fuels can cover this demand. So one example would be the different processes to produce steel, and right now we set this exogenously in the model, but we might include the decision which process to use for the steel making inside the optimization problem formulation. We also want to look at the reallocation of industry and options for imports and what it means for the import infrastructure that we need in Europe, as well as CO2 infrastructure, so pipelines, sequestration potentials, and so geological sequestration potentials, and where carbon sources could be. On a more technical side, we want to improve a little bit on how scenarios are managed within the conflict of YAML, so that you can easily sweep a lot of different scenarios with a lot of different parameter settings to account better of the myriad uncertainties involved in energy system modeling. And we definitely also need to improve a little bit on the documentation, and the team at Aarhus University is currently tackling that. So these are roughly the talking points for the next upcoming months to year.
Great, thanks a lot, Fabian Squared. That was a very nice overview. I will actually quickly shut down the meeting so people can go for lunch, but maybe just a few final words. I want to thank all of our speakers who've taken the time today to prepare. Well, they've prepared their talks and given the talks, so I really appreciate that you've all come to give those such interesting talks. You know, we said we'd only have 10, but they were also interesting. We had to do 13. We took all of them because they all looked good, and I'm glad we did, but it's been a bit of a long morning, I have to acknowledge as well. But it's triggered lots of good discussions and lots of sharing, and it really shows the benefits of the open ethos, that everyone's very happy to exchange. We've seen in the chat lots of connections being made, which is, I think, one of the main purposes of the meeting, is to get people connected and helping each other. So thanks a lot to everybody. Particularly big thank you, of course, to Christoph, who actually did all of the organization and all of the moderation. It's a lot of work behind the scenes, coordinating with all the talk people, and really big thank you. It's run really smoothly. So thanks a lot, Christoph, for taking over that work. And yeah, thank you all. And I think, Christoph, there's some informal meeting room now, so I'll hand back to you for that. And thanks, everybody.